and the special invitee whosoever joined this evening. Now it is my privilege to welcome the first speaker of the today's session, Dr. Chinmoy Shah, Associate Professor from Indian Institute of Space Science and Technology, Trivandrum, India. Chinmoy Shah received his BTech, MTech, and PhD degree in radio physics and electronics from Calcutta, from University of Calcutta, India in 2002, 2005, and 2012 respectively. He is currently working as an associate professor in the Department of Avionics, Indian Institute of Space Science and Technology, Department of Space, Government of India. He has visited several international universities of repute like Royal Military College of Canada, Royal Military College of Canada, and University of Alberta, Canada. He is senior member of the IEEE and life member of IET. He is the founding and current chairman of IEEE MTTS Kerala chapter. He has served as the chairman of Antennas and Propagation chapter of IEEE Calcutta section during 2018-2019. He has received several prestigious awards, which includes Outstanding Teacher Award of IIST in 2019, National Scholarship from Ministry of Human Resource Development, from Government of India, Outstanding Contribution Award from the AP-MTT Calcutta chapter, Best Contribution Award for Notable Services and Significant Contributions towards the Advancement of IEEE and Engineering Profession from IEEE Calcutta section, and several Best Paper Awards in various international conferences. His current research interest includes wireless power transfer and energy harvesting, channel modeling for wideband and ultra-wideband systems, microwave circuits, engineered materials, metamaterials-inspired antennas and circuits, reconfigurable and multifunctional antennas for modern wireless applications, dielectric resonator antennas, and terahertz antennas. He has more than 100 publications in peer-reviewed national and international journals and conference proceedings, and authored 2 books with Cambridge University Press. He is on the board of reviewers of several international journals of repute, including IEEE Transaction on Microwave Theory and Techniques, IEEE Transactions on Antennas and Propagation, IEEE Antennas and Wireless Propagation Letters, IET Microwaves, Antennas and Propagation, Electronics Letters, etc. He is an associate editor in IEEE Access, an international journal of RF and microwave computer aided engineering, Wiley, and guest editor-in-chief for an ongoing special issue in the same journal. With this, I invite you, Dr. Shah, as the first speaker of second day session to start your talk. Dr. Shah, please. Professor Shah, you are not audible. Your microphone is mute. Okay, now.
Yeah. Am I audible now?
Yeah, you are audible now.
Yeah. So firstly, thank you very much, Dr. Toimur, for the nice introduction about me. And I sincerely congratulate you for taking this special initiative in very tough time. All of us are facing. It's a global issue, the pandemic. And I can understand how much involvement this type of workshop takes place, even though it is in a virtual mode. Then also there are a lot of formalities, a lot of things, the way the entire program is coming up and panning up, it's definitely deserves special applause. And also I extend my sincere thanks to the director of the institute, other faculty members, and of course to the participants over online for their overwhelming response, because I have got a lot of feedback from yesterday's event itself, I mean yesterday's version itself, that this is a very useful workshop, because we see from different networks that a lot of webinars and all are going to happen and already happened in last few days and coming up also. But this type of focused workshop, that too under an umbrella of Indo-Canadian workshop, under the umbrella of GST Inspired, is something which is quite unique. And I feel this may be one of the rare events of GST SPARC workshop, which is happening in virtual mode. Incidentally, in the month of February, just when the we are in the onset of the pandemic phase, especially in terms of India. Maybe that was peak for in some other countries. I was one of the speakers for another DST SPARC workshop which happened in NIT Silchar. Anyway, with this small introduction, I'll go to the agenda, which is the presentation. Even though this particular workshop is titled in the name of, is my screen visible?
No, your screen is not visible to us.
Just a minute. Is it visible now?
It is coming now, I think. Yes. Yeah.
So as I was mentioning, even though this particular workshop is in the name of RF energy harvesting systems, I have decided my talk in the other part of the coin, which is just if you flip this particular problem, then you know that very much associated with the energy harvesting is the oil-filled wireless power transfer, near and far field wireless power transfer. So this particular topic that I am going to discuss next 1.5 hours is basically outcome of a very fruitful interaction with Professor Yahya Antar and my industry collaborators, or my very close friend who I got in touch with him after during my visit in 2017 and 18 at RMC Canada. So which was basically some new kind of technique, new type of materials for proposing wireless power transfer using dielectric materials and split cavity resonators. As far as the topic energy harvesting is concerned, as you know, the energy harvesting means we need to have proper antenna, circuit systems, and all together. But we are to rely on the ambient power. I mean, as far as the RF energy is concerned, even though it is omnipresent, it is present everywhere, it is present every time, but you are not sure regarding the power level, regarding the intensity level, or regarding the direction where it is coming from. So sometimes in certain situations, we need to transfer the power in certain directions, especially the biomedical gadgets and the wireless, the electric vehicles are coming, which will be based on not only coming, few models are already there, which are based on the wireless power transfer concept. So considering this particular aspect, I just want to brief about the harvesting aspect as well as some of the works that we have done in collaboration in the field of wireless power transfer. Because of the global audience, I believe I take this opportunity to introduce my institute, IIST Trivandrum. As you can see, it is at the extreme southern part of India, at the close in the region of Arabian Sea, Trivandrum. And this particular institute was initiated in 2007 by Missile Man of India, and later on he became the President of India, Dr. APJ Abdul Kalam, with a particular mission and vision to produce quality human resources for Indian research organization. And I'm a bit proud to say that as of now, almost 1,000 of our former students are working Indian Space Research Organization and scientists in different labs, in different labs of Indian Space Research Organization, including URL Satellite Center, Space Application Center, National Remote Sensing Center, Hyderabad, and so on and so forth. I take this opportunity to introduce the different research activities that's happening in a group. Many of these activities are in collaboration with Professor Yahya and Professor Siddiqui and a few other labs from ISRO centers as well. So we predominantly work in the area of printed antenna research, where we have done quite a bit of work on ultra-wideband antennas, reconfigurable and multifunctional antennas. Then we are doing some kind of massive MIMO kind of applications where we are thinking of employing SIW circuits and concepts, and then metamaterial inspired surfaces or antennas, and then GRA based antennas. And today some of those applications, even though it's not directly antennas but rather high Q resonators, I'm going to discuss on that. And then, as I mentioned, being a part of the Indian space mission, we do a lot of collaborative work with different space research centers. Like some of those works are basically designing feed antennas for satellite tracking applications. Then very recently, we have worked on some new kind of antennas for national remote sensing centers in collaboration with them. And then also for different reusable launch vehicles type of applications, we are working on printed and conformal type of antennas. And this is the last leg of our research that's happening in our group. As far as the millimeter wave and terahertz systems are concerned, we are trying to do some work on terahertz antennas also, especially the photoconductive type of antennas. Doing this particular type of research sitting in India is not very easy as of now because of huge infrastructure and huge facilities required. But we are collaborating with few IITs, and we are in proper touch to come up with some good quality work in this particular area also. So I again take this opportunity to introduce some of the research topics, some of the glimpses of research activities that had happened in our group over last few years. So I'll just have a virtual tour to introduce this particular work with the audience. So these are some of the printed antennas that we have developed, the new techniques of designing ultra-wideband frequency notched antennas using split ring resonators loaded beneath the feed line of the CPW fed antennas, and then improvise those techniques later on to come up with dual complementary antennas. And some of these works are published in very reputed journals, as you can see, IEEE transactions and IEEE antennas and wireless propagation letters. So this one is a very completely new concept where we have for the first time shown that a single antenna, which is a printed monopole, that particular antenna is nothing new. I mean, was proposed around 2004 and 5 after the FCC recommended the 3.1 to 10.6 gig as ultra-wideband, but the same antenna with different kind of tuning with split ring resonators and diodes, in the pin diodes and the varactor switches and so on and so forth, you can make the antenna reconfigure in different modes. So we named this antenna as a dual complementary antenna or multifunctional antenna. This is some collaboration with National Remote Sensing Center, Bikram Sarabhai Space Center, and NIST, which is National Institute of Interdisciplinary Science and Technology. As you remember, during yesterday's talk, Professor Yahya Antar was mentioning about the Professor Sebastian at NIST. So in fact, some of these dielectric resonators we got from his lab, and we have used some improvised technique. I mean, by combining the monopole, normal monopole, I mean, rod monopole, which is erected from a ground plane vertically and surrounding that with a dielectric resonators, you can achieve very ultra-wideband antennas. And some of these ultra-wideband antennas will be very much useful for today's topic that we are going to discuss over this particular week, that is the energy harvesting. As we have more and more wideband antennas, of course, there is a, I mean, we are scanning the power over a wideband, so there is a higher power that we can scavenge from the atmosphere. But it is not only the antenna, we have to think of the other subsystems, especially the rectifier circuits, the matching circuit and all. So on antenna fronts, definitely ultra-wideband antennas or wideband antennas, or at least multi-band antennas will be very useful. So this is some of the work that we do on using the metamaterial concepts. I won't say these are metamaterials, because material is a concept where you need to have homogeneous medium and I mean, quite a periodic circuits, but these are some pieces of resonators, split ring resonators, which are loaded in a engineered medium, kind of medium on the feed line of the antennas. As you can see on a Vivaldi antenna, when you load these kind of resonators, which are called split ring resonators, and or a horn antenna, or even some dielectric resonator antennas, you can come up with different kind of functionalities, different kind of features evolving from the same antenna. This is another very interesting wing of research, which is basically antennas for cognitive radio applications. As you know, cognitive radios are a very one of the new concepts in wireless technology. And the CR, or the cognitive radio, is basically an intelligent radio. And as the word cognition suggests, I mean, it is something which is capable to understand the scenario, understand the spectrum scenario, and observing the available spectrum at that particular moment in a dynamic fashion. The secondary user is allocated to the available spectrum. So this calls for multiple antennas. I mean, one for frequency scanning to check where is the available spectrum free now, and then secondary antenna which will be communicating in that available spectrum in a dynamic fashion. But without using multiple antennas, we showed a particular solution where a single antenna can do the frequency scanning. The ultra-wideband mode will be giving the frequency scanning, and the resonators were loaded with the varactor diodes and with the switches, and then turned on and turned off. The same antenna can scan between the two modes, that is the ultra-wideband mode or frequency-notched ultra-wideband modes for observing the idle spectrum, and then the communicating mode for communicating over the available bandwidth. This is the front page of the publication very recently in IEEE Antennas and Wireless Propagation magazine. And these are the some of the experimental setup which incidentally we did at Royal Military College of Canada with the support with Professor Frondhofer from Queen's University, who is also one of the speakers and one of the key persons involved in this particular workshop. And this is something, as I was mentioning, that by using different kind of concepts with different kind of microcontroller and switches, and using the resonators, and then having some rectilinear motion actuated through this motor and Arduino controller, you can actually make sure that the same antenna can give different kind of responses. As you can see over here, that this is a narrowband antenna, but it is frequency reconfigurable narrowband antenna, and this frequency reconfiguration is because of this actuation of different kind of split ring resonators and different kind of switches which are loaded in this particular antenna. This is some kind of experimental setup. On the other hand, the same antenna, when the switches are in off condition, then you get basically these combinations, that is the frequency notched ultra-wideband configurations at different frequencies, f1, f2, and f3, and so on and so forth. This is the new part, which is we have started just a couple of years back, photoconductive antennas. As I was mentioning at the very beginning, that these antennas are completely different ball game, because these are not printed on a dielectric substrate, rather these are printed on a semiconductor substrate. So this is basically a LT gallium arsenide, or some material having very high mobility and very low minority carrier lifetime, and these are actuated through a laser beam. So when the laser beam shines the semiconductor, you actually converts the photons into electrons, and there is a transient current formed over here, and that transient current actually gives rise to the radiation. So using this kind of concept, we have developed some very high gain antennas, and for this type of work we have collaborated with Space Applications Center, Ahmedabad, our sister concern under NIT Space Research Organizations, and some of the measurement facility, even though we are not having, we could do from the Indian eyes at Trivandrum. And then, as I mentioned, because these are on semiconductors, so it is not only the antenna engineering, it is actually combination of few concepts, because you need to have a solid idea on nanoelectronics, and you need to have the photonics concept, because you have the photons and the laser beams, femtosecond laser beams, which are exciting the antenna, and of course a solid background on the material science, because you need to know which semiconductor, compound semiconductor, of course, it is needed, and what is there, how you can tailor their mobility, how you can come up with a proper minority carrier lifetime, so that you can get the terahertz radiation in the particular frequency, between 300 gigahertz and above, maybe 1000 or above. So we did some work with 500 gigahertz in mind, and we have designed some antennas. Anyway, today is not the day to talk about this, but I'm just giving an idea that our institute has taken a long-term vision of establishing some of the facilities in this particular area, and we are in the process. So as I mentioned, we have designed and developed some of those antennas. As you can see, this is basically the SEM image of those fabricated antennas, which is many thousand times magnified, because these are just micron and nano devices. So, and in fact, in IIC Bangalore, and during a conference at IMARC Ahmedabad, our idea and our initial idea was given the best paper award. This is some work that we started with Professor Yahya Antar when I was visiting 2017 and 18 at Royal Military College of Canada. This is something I'll be going into details today, so I'll probably skip this particular slide. And as I mentioned, being a part of Indian space mission, we do some work for space antennas. So this is maybe some basic antennas in terms of the basic design, but application is different. This is for a reusable launch vehicle type of applications, so different kind of linear and circularly polarized antenna. But most importantly, it has to be reconfigured and conformal depending on the size and shape of the launch vehicle. So some of those things are there, but this is a very interesting thing. As you know, that satellite tracking is a very important concept, and tracking involves communication to receive the data from the satellite, and also to make sure that the ground station antenna and the satellite antenna is looking towards each other. So as you know, that monopulse tracking is one of the fundamental concepts, but very recently we are doing some work so to receive satellite data in a much faster rate. That is a tri-band tracking, we call it. So simultaneously the data can be received at S-band, X-band, and Ka-band. This is a X-band basic design, but the advanced design are also in the pipeline. So this is basically the SAM antenna, which is receiving the data from the satellite, and these are the four polarizers A, B, and CD, which are, I mean, A or B are basically, towards the elevation, whereas C and D are towards the azimuth. And these four antennas together receives the signal along with the SAM, which is supposed to receive the data. And by combining these signals, especially A, B, and CD, the tracking part is taken care. So when A and B is receiving different signal, that indicates there is a elevation error, or if C and D are receiving different signal, I mean, there is a different signal getting generated, that means there is an azimuth error. Then depending on these error available, and using this circuit concept and the signal processing concept, actually this particular part will be going to a servo, and that servo will be actually controlling this motion. And accordingly, we have to make sure that the SAM antenna is always looking towards the satellite. So ideal condition, A, B, and C and D will be receiving same signal, so there is no elevation or azimuth error, and then you get the SAM pattern like this, which is a very high gain beam, around more than 30 or 35 dBi sometimes, okay, by exciting proper mode in the horn. So this is looking towards the satellite, and this is the difference pattern. When there is a difference getting generated, I mean, this, if null is not along the axis of the horn, then you will have this elevation or azimuth error. Accordingly, your system will adjust yourself, maneuver itself, and accordingly you again make sure that your servo system gives proper pulse and your antenna is aligned towards the satellite antenna. So these are some of the work which is not again directly related to today's theme, but as I mentioned, that for energy harvesting also, ultra wideband antennas are very important, and new antenna research, especially in the front of MIMO and massive MIMO, it might not be directly linked with the today's concept, but definitely the massive MIMO or the many number of antennas employed or deployed together on some substrate or in a circumferential fashion is going to have a lot of implications towards the concept that we are going to discuss over this week-long workshop. So this is just a kind of idea that I was discussing earlier, cognitive radio, that depending on the available spectrum, you have to make sure that your secondary antenna is actually communicating in the range you are available. So with this very brief virtual tour regarding the research happening in our group, I go into the outline of today's presentation, even though I'll be talking mostly on the wireless SPARC transfer and the new work that we initiated recently, and I published some amount of that work, and some are in pipeline, but I'll be giving a very broad overview of energy harvesting and then basics of RF energy harvesting, and then I mean, most of the time I'll be discussing the wireless SPARC transfer. Sorry. Coming back to the agenda, the energy problem, as we know, for many applications we need sustainable and environmental benign energy sources. And of course, even though we are talking about the RF energy sources today, but if we see the different options, the option is not only RF energies, but there are many other ambient energies also. For example, we have solar energy, we have wind energy, and of course tides. So even though there is a specific advantage with respect to the RF energy harvesting, but there are some issues also, because these are very low power applications. You won't get very high power in the situation that sometimes we need for, but there is other mechanisms to combat that particular concept. Especially low power applications are it has applications in biomedical applications, different sensors, IoTs, and so on and so forth. So RF energy is basically for small power applications. So for the beginners who are just going to start their research career in this particular field, you might be aware of, or you should try to be aware of, that what is energy harvesting. It is basically a process that captures small amount of energy that would otherwise be lost as dissipated. I mean, it would be dissipated in different forms. It may be heat, it may be light, sound, or whatever the different forms of energies are available. So the main idea is, when we try to harvest or scavenge those power, we have to ensure improved efficiency, that is conversion efficiency, because the power is available in other form, energy is available in other form. We are trying to convert it into usable form. That is ultimately, probably, if we want to try to operate a load, we'll try to convert it into a DC signal. Okay, and we have to think of different new technologies. And as far as the RF energies are concerned, RF harvesting is concerned, so there are, as I mentioned earlier, the main applications will be some small power applications, where there are many situations for working with those who works on IoTs and wireless sensor nodes. They know that many sensors are deployed in different kind of scenarios, and those sensors actually requires the periodic replacement of the battery. So even though that requires very small power, but periodic replacement is very much important, and that's quite a complicated job. So if we have a inbuilt system which are deployed along with the sensors, then we can harvest the energy, scavenge the RF energy, and that microwatt or nanowatt level of power is adequate enough to run the show. Okay, so the main advantage is, when we deploy this in our situation in the actual applications, it is maintenance free. Once it is deployed, you don't have to have a regular day-to-day replacement or day-to-day operation. It will be omnipresent, because you are harvesting from ambient. Then it is, of course, environment friendly, and there are many other applications we can think of. So where do we look for this energy or the power? So one is the power stations, and then of course the microwaves, the computer networks, microwaves, and even we know that human body also radiates the energy or power in maybe in different spectrum. But there is, in fact, as you know from the fundamental physics, whenever you have a temperature, any body which is not absolutely cold body, even the cooler body radiates terahertz signal. So any body which is not at T equal to 0 Kelvin, as you know, according to thermodynamics principle, T equal to 0 Kelvin is unachievable. So any temperature, finite temperature body will have some radiation, but we have to see which one is friendlier, which one is meaningful, which one is has some meaning to harvest, and we'll get sizable amount of power depending on the applications. So these are some of the sources of energy that we can try to harvest. Light energy from sunlight to or artificial light, because it is the natural sources. Then we have the kinetic energy. There are many work which is going on, especially by aerospace engineers or mechanical engineers, who are trying to harvest mechanical stress or strain, or there you need to apply the piezoelectric effect, because if you have vibration, and using the piezoelectric effect you can convert the mechanical vibration into electrical signals. And then we have the thermal energy, which is basically, if we don't harvest in a proper manner, it will be going to be dissipated as heats or friction, and then the options that we RF engineers look for is the ambient RF energy. So this is again a functional block diagram. So as we have different mechanisms, I am not specifically telling that these are antennas, but these may be other thing also, because we can harvest from different ways. It may be some metasurface kind of structures also. But once you are harvesting, that means you are converting your, you are receiving the harvest signal. Your job is not done. It is just started rather, because we have to convert this signal in a proper domain. So there are conversion circuits. So these may be rectifiers, it may be some multipliers, or some voltage doubler or voltage tripler or quadrupler kind of circuits. But that's not enough. Then we have to make sure whatever you have harvested is not dissipated, rather it is stored in a proper fashion. So here calls for a high Q circuit or high Q element. As Professor Antaroaz started mentioning, that dielectric resonators are one of the good candidates because of their high quality factor. So we need to make sure that through some capacitor bank or through some dielectric high quality factor dielectric resonators, or by ensuring that our circuit won't have radiation losses and other thing, because through radiation we have got the energy, and then we don't want that energy to get dissipated through another radiation. So this is a kind of feedback loop. We have to make sure that this PMC unit, that is the power management control unit, is working in a proper fashion, and then finally that energy that you are storing is going to the electronic load. Sorry. So as I mentioned, so these consist of these blocks, that is the harvesters or transducers, then conversion circuits. When you go to a particular application or a particular sub-circuit, this conversion circuit will be basically rectifiers or multipliers, and then you have the energy storage unit, and then the power management control. So now I'll be spending around maybe 10 to 15 minutes on basics of RF energy harvesting, and then we'll be going to the work that we have done in collaboration. So why RF harvesting? As I mentioned earlier, that this is the main advantage is it is omnipresent. It is not limited to space or time. It is there everywhere, wherever the God is there, electromagnetic signal is there. So we have the option to harvest the RF energy. So despite its low power density, there are some applications, especially as I mentioned a few minutes before, that it can be deployed in wireless sensors network and IoTs, but there are very interesting medical applications also, especially on embedded antennas or some kind of, especially for body area network, for medical, not diagnosis, for diagnosis also, for some kind of capsule endoscopy kind of applications. These WPTs are important, even in our hearing aids also. Those who are having some disability or partial disability in hearing, so they are having some kind of small gadgets, electronic gadgets embedded, so that without going for a second surgery, you can actually make sure that the power is transferred, and then especially for pacemaker kind of applications. But the fundamental limitation we must accept, before going to this thing, it is better we know what's the problem. But so the main limitation is the tiny amount of power can be harvested. So we need to think of how we can come up with this solution, but it is very good for low power applications. So these are the different kind of harvesting concepts, as we have kind of given an overview. Thermoelectric, which is thermal energy to electrical energy. As we know, the class 2 physics, the Seebeck effect, wherever there is a temperature difference created between two junctions, two metallic junctions or metal semiconductor junctions, the temperature gradient actually creates a voltage, and that is basically a thermal to electrical conversion. Then, as I mentioned, the vibration or mechanical stress or strain can be used in a proper manner, even in acute acoustic noise and or different kind of supersonic noise or whatever it is. Whenever you have a kinetic energy, that can be converted into electrical energy using the piezoelectric effect, because that is the fundamental principle of piezoelectric crystals. And then we have photovoltaic, where you actually the name is obvious and the meaning is clear from the name itself. Photo to volt, that is from light, you are basically converting electrical energy. So this is very, very useful for as you know, in the satellite payloads for operation, long-term operation, we deploy these solar cells, and then portable power supplies, street lights, and so on and so forth. And then RF energy, RF, of course, because we were having the RF, and then we have to down convert, so we'll be converting it into electrical energy. If you compare these different options, then whatever I mentioned, that is the solar, vibration, and thermal and RF, then as I mentioned, that as you can see over here, that for two bands, if you consider the GSM band or the Wi-Fi band, okay, so the power level, as you can see, with respect to the other options, especially the solar or especially the thermal aspect, so this is always in the lower side, okay. And RF will be even though it's mentioned only antennas here, but along with the antennas, as some of the speakers are enlightening in that particular area, the metasurface based harvesters also possible, but that is the first block. So we are converting, we are receiving the RF signal, but the next of the circuit work is due. And then you can compare with respect to other aspect, what are the advantages, and but the main disadvantages, as we have already mentioned, that these are the limitations we have to accept. This is a generic block diagram for RF energy harvesting. So the key units are antennas, matching circuits, and rectifier circuits. This is pretty clear. The conceptual block diagram, you have the omnipresent RF signals, you're receiving antenna, whether, on antenna front, not a lot of new research is going to happen, because what are the different types of antennas, and depending on which band you are going to harvest, you can decide your antenna whether it is narrow band harvesting or wide band harvesting. So you can have your proper antennas over here. You can have different kind of solutions, but the next part becomes complicated. If you're the first stage, that is the your antenna stage, is a wide band and ultra wide band, because you have to make sure your matching is also wide band and ultra wide band. Some work are happening, some good works are already published in this particular area, so you have to have a proper matching network. And so this block together, the antenna and the rectifier together, we call it as a rectenna. And as I mentioned earlier, this is the power management unit, so you have to make sure that it is converted in a proper fashion, and then it is stored, and before it finally is delivered to the load. So when you convert, think of the efficiency, antenna engineers efficiency is a straightforward efficiency, because we know how much is the power and how much is the radiated power and how much is the input power. Based on that, we can define the efficiency. But here first block is converting RF into the DC, and then from DC you have to make sure that after rectification, after reducing the ripples, you have to finally giving to the load how much you are giving to the load. Okay, so depending on the applications, this particular concept can be divided again into two categories. One is the near field category and another is the far field category. So when you have a RF energy harvester, so you need certain matrices to evaluate its performance, the figure of merit. So these are predominantly, even though there may be few other sub parameters coming into picture, but these are the main parameters by which we evaluate the performance of a RF harvester. One is the operation range, like what up to what frequency or up to what distance we can operate. So if we really want to make sure that of course, as we go to the high frequency, as you know that at higher frequencies there will be more attenuation. So some people want to have want to work in the megahertz range or lower frequency range. The size of the circuit will also depend on which frequency you are working, and depending on the as you know the 2d square by lambda formula, that is the Fresnel and Fraunhofer Roentgen. Depending on the frequency of operation, you can decide whether what is your near field and far field transition, and then you can deploy one of the techniques, and accordingly you can have an idea regarding your transfer distance or regarding the operation range. This is very important. The second point, RF to DC power conversion efficiency. This equation, as you can see, it's not just a combination of RF to AC, because first you are having RF and then you are converting into alternating current, but then you have to convert again into AC to DC. So this part is basically the rectifiers. Not only the rectifiers, normally along with the rectifiers you will have the other components like multipliers and so on and so forth. Okay, so this is the expression for the total efficiency. So we have to make sure our antennas are good, matching circuit is good, and finally the rectifier circuits and the power management unit is also very good. And then in terms of the power collected and RF input, in terms of power, it is these two equations are basically, they mean same, but this is in terms of the fundamental raw power, and this is in terms of product of the two efficiencies. So the first ratio is actually eta RF to DC, and the second ratio is eta AC to DC. And then most importantly, especially for dielectric resonator based harvesting or metasurface based harvesting, this parameter takes a key role, that is the resonant Q factor. So this is very fundamental. As we know, the Q is defined in terms of the energy storing capability to the energy getting dissipated. So it is FC by delta F. So we have to make sure that the circuit or the resonators or whatever it is operated at a very high Q. Especially when you are observing or working with dielectric resonators, you have to make sure you are exciting the proper modes. You are exciting with a mode which is having high quality factor, which will be ensuring a good storage capacity, because energy loss will be leading to low Q, so energy loss can be minimized sometimes by adding reactive components. Here sometimes antenna engineers always try to do 50-ohm matching, but here the total matching will be the matching of the just not the antenna, but matching with the rectifier circuits and the next sub circuits. So sometimes we deliberately use some reactive components so that some conjugate matching or something like that is possible, because overall ultimate impedance has to be 50 ohm, not just the antenna impedance to be 50 ohm, because the rectifier circuits sometimes gives rise to inductive and capacitive capacitances. Quite a lot, the reactive components. And then sensitivity, this is very important because minimum power required for trigger that harvesting energy system, that is called the sensitivity. So it is something the to cross the cutoff. So below that cutoff, below a certain level, your circuit will not sense, and of course then we'll have the fundamental limitations. And then of course the output power. So as far as the antenna design part is concerned, which is the fundamental or the first block for energy harvesting, as we know that there are different choices of antennas. These are some of the choices which have been reported over the last few years. There are quite a lot, but these are a few examples I've just taken for the beginners. So when you design the antenna, as you know, that gain, resonance frequency, bandwidth, polarization, sometimes you can go for dual polarized antenna so that you can harvest both the components of the power. And then depending on the sizes and applications, if you want your harvester circuit to be embedded inside a wireless sensor network or some biomedical implanted devices and stuff like that, then probably you need to have on-chip antennas or system on substrate or system concept over there. There is nano-sized antenna you have to deploy. Okay, so of course there will be issues with respect to efficiency and all, but then there is some advantage with narrowband antenna, because when you work with the narrowband antenna, the rest of the workload becomes simpler, matching becomes simpler, and then rectification and all also becomes simpler. But the main thing is with narrowband antennas, you will be harvesting only over certain range. Maybe you are harvesting only GSM or Wi-Fi or so on and so forth. So you won't exploit or leverage the full potential, the RF energy, which is distributed over quite a few bands. And then we can think of the array antennas. And then when you have the array antenna, there are two concepts actually. You can have the array first, and then you have power combiner network, and then you have the rectifier circuits. But then you can have individual antennas also initially, and then you can combine that also. So these are the two choices available. This is very basic. I'm going to talk about the impedance matching network, because I'll be now want to go into the part that where we have contributed. So these are available impedance matching network, because you have to match your antenna with the rest of the circuits, especially the rectifier circuit. So these are some of the choices. As you know, this is very fundamental of electromagnetic engineering. You have L matching or reversed L network, and then T network and pi network. Depending on your situation, you have to deploy one of the matching circuits over here. And then the next important block is the circuits, which are basically the conversion circuits, which are rectifiers. There are quite a few choices of rectifier topologies. These are very basic thing. Only thing, the same +2 level physics applies over here. You have the half wave rectifier circuit, and then full wave rectifier circuit with voltage doubling capability through this network, through this capacitive block, and you have the bridge rectifier circuit. Of course, only thing is these diodes has to be compatible with a very high frequency you're operating. So you cannot just use any normal PN junction diode. You have to have the compatible diodes, and you have to, of course, go for a better topology, not with the half wave rectifier topology. And then within a given topology also, there are few choices. Like you can go for series diode topology rectifier. Series diode topology is normally used when in some applications the power level are low. If you do some basic analysis, circuit level analysis, or circuit simulation using ADS or stuff like that, you can generate some response from the circuit. So series diode configuration has these and these features. So for low power application or a low threshold voltage are required, we can deploy these. And then we have shunt diode configuration. These are good for high power applications, and diode with hard breakdown is required over here. And this is basically voltage doubler configuration So it consists of one diode, as you can see, in series and another in shunt configuration. So this is a combination of the first two concept and then some other ideas. So it can have full bridge configuration, or it can doubles the output voltage and hence the power. So these are conversion circuits, which are basically multipliers. So these are basically, again, the microelectronic circuit kind of thing. So you can go for different choices of conversion circuits, which are basically high frequency multiplier circuits. We can have Cockcroft to Alton. Then Dixon amplifier is quite famous. Then you can have modified Dixon multiplier, and then you can have MOSFET topologies and so on and so forth. So with this, I'll just have a comparative table over here. So if you compare some of the articles that I'll be showing at the references, which have been reported over last few years, with respect to frequency of operation, with respect to the technologies they have used, as you can see that most of them, I mean, all of them, in fact, have used the CMOS technology, and then power conversion efficiency. So when those who are at the beginners, they should have a thorough literature survey with respect to the different topologies, with respect to the circuits, and then you have to see, because as you can see, most of these are at quite a single band or narrow band application. So an antenna front, that will be simpler. And then, as I mentioned, the next step will be the power management circuit. Okay, so with this particular part of the talk, I conclude that RF energy harvesting, even though there are a lot of concepts of energy harvesting, RF energy harvesting is a specialized field which has to be contributed by the RF engineers, and it involves quite a bit of involved research in designing antennas. I mean, especially when you're trying to aim to harvest over a wide band or ultra wide band, we have to have a challenging problem in terms of choosing a proper matching circuit and the other component, as I mentioned, the multipliers and associated stuff like that. But limitation we have to probably accept, because we can't go for a very high power until and unless we have a special kind of improvisation. So main applications will be wireless sensor network, IoT based devices, and biomedical applications. So with this, I come to the second part of the talk, which is WPT, wireless power transfer. So I will have a very basic introduction about the WPTs. In fact, if you see the chronology in terms of literature, then this WPT is in fact not a very new concept. In fact, there have been various attempts since 1890s. I mean, I was trying to do some kind of in-depth literature when I started in this field. So it was a kind of 10-year timeline, 1890 to 1900, and then during this time frame, there was a lot of breakthroughs, but probably the requirement or civilization requirement was not that much. But after this 2008 and 2010, especially after the different automobile industries came up with different kind of models where they want to have the wireless charging of the vehicles, this particular research has completely taken a different shape, as it will be evident from a slide which is going to come very soon. So these are some landmarks in the area of wireless power transfer. 1830 is the Faraday's law of electromagnetic induction. As we know, whatever we do, if we want to transfer by by induction, then it is the Lenz's law and Newman's law, which together is Faraday's law of electromagnetic induction. So this is the kind of concept, a coil, and through the coil, by inductive coupling, you can transfer some power. And this was the Tesla's dream. 1890s, he designed a big system to make sure of transferring power over 100-meter distance. There is some controversy over that thing. Anyway, then around 1990s, the first inductive charging based electric vehicles was proposed, and this is quite involved work, and it has it already there are quite models which are coming with this, and in our country also it is going to come very soon. So but as far as the lab research is concerned, the breakthrough came in 2007. Sorry, one research group under the MIT and Professor Alanson Sample also, they together actually did a research which shows that a 60 watt 2 meter inside the lab using long big coils, as you can see here and here. A power transfer was first time demonstrated, but the coils, the operation was done, the transfer was done at a very low frequency, probably in the range of kilohertz, and that's why it required very big coils with a radius of more than meters. And then 2010 onwards, there are plethora applications coming into the picture: wireless chargers, and then commercial, different kind of commercial devices. In fact, some applications, as I will be showing, very interesting biomedical applications also. This is a very interesting slide because this was even though I'm now showing it in 2020, but this was a futuristic a prediction. Okay, so this shows that basically amount of investment on the revenue that is going to come through this WPT. So if you see it, you see that this is kind of having a complete exponential growth. In fact, again, each of these revenue is divided into different components. So the mobile devices, then consumer electronics, then EVs, the electric vehicles. As you can see, as time passes, the EV component is also getting bigger. Okay, and then we have industry applications, and then it has military applications also. And these are some of the the models of vehicles or the automobile industry who are coming with these embedded electric vehicles, where the power transfer can have through the inductive coupling or near field wireless power transfer, whatever it is. You see almost all the big shots, starting from Audi to Chevrolet to Ford to Hyundai to Toyota and so on and so forth. Almost all the big shots are there. Okay, so this says that we need to have a proper idea, proper mechanisms, and applications, keeping the proper focus in the applications. We have to come up with different kind of technologies. So these demands for is increasing exponentially. In fact, in this regard, I just want to mention that IEEE Microwave Theory and Technique Society has also taken a new initiative in terms of a completely new conference which focus only on WPT, that wireless power transfer conference. In fact, while I was in RMC during that time, I attended one of the versions of the WPT conference, which was in Montreal. And in fact, there are so many presenters, especially from industry front and academia, of course. So this is a thrust area MTTS has identified. And in fact, Wireless Week, wireless power transfer conference, and probably some other conference of the MTT were co-organized in the Ecole Polytechnique Montreal under the same building. It was quite a big conference, and there are quite a few hundreds of papers in WPTC track itself. Wireless power transfer track itself. Coming to the introduction on WPT, there are two concepts. One is the near field concepts, another is the far field concepts, and the applications are quite involved now. It is evolving more and more. We have near field communication, NFC. One of the applications is RFID, radio frequency identification. I think Dr. Siddiqui, who is one of the speakers, probably tomorrow or day after, is going to enlighten more into this direction. I'll be involving more into the WPTs. So this is another interesting applications of WPT. You might think that it is quite challenging. Yes, it is challenging, but this is a need of the hour, because there are a lot of surgeries, a lot of embedded electronics getting inside our body nowadays, starting from pacemaker to hearing aids, as I mentioned earlier. Okay, so here sometimes what happens, just to replace the battery of the pacemaker, the person has to go for a second surgery. So we know that the transferring power through the medium and through the body, which involves quite a complicated medium, because you have skin, fat, and then of course the highly lossy saline water and so on and so forth. Transferring power in that mode is very, very complicated and probably very low efficient. But forget about the efficiency, because that requires a very less amount of power. Even microwatt or that level of power is sufficient. So with a very low efficiency, even if whatever efficiency is getting sacrificed, if we can transfer the power and we can energize the battery again, probably we can get rid of the second surgery. And this is another interesting applications. As you know, these embedded antennas and the on-body antennas is coming up very nicely, where you have different kind of antennas which are embedded inside the body, or even some kind of medical diagnosis also. Now they are using different kind of capsule antennas which is going through the electronic stethoscope or electronic gadgets kind of thing. So here actually once the antenna is embedded, how do you make sure that the circuit part is operational? Because this antenna, embedded antenna, is actually going to communicate with another antenna which is on-body antenna, and that on-body antenna, it will be receiving the body data for patient monitoring kind of application. So body data will be received by the on-body antenna, and then that antenna, that particular person, through the communication by that antenna, will be connected to the network, which is the communication to the nearby hospitals. I mean, so that of course the data might be in cloud also for anytime use. But the problem is that embedded antenna and the associated circuit, which is basically, it might be a sensor, it may be a glucose sensor or any other kind of sensor that captures the body signals, it needs to be energized. It requires very less amount of power, but it needs to be energized. There also the WPT can have quite a big implications. As far as the power level is concerned, so when you are doing medical devices and sensor network kind of thing, or the sensor network type thing, actually your power requirement is not very high. Microwatt or milliwatt type of power is enough for that medical kind of applications I was talking about. But then when you come to consumer electronics, the requirement is more. And of course, when you're going to transport system and the automobile industry I talked about, the requirement is even more. So you need a kilowatt or other kind of, more amount of power. So this is a kind of different kind of WPT methods that have been reported since quite after Aronson sample did this inductive coupling experiment, and then a few groups have reported some other kind of work. So if you compare the different kind of techniques of WPTs, then you can actually come up with this kind of table. So inductive coupling, then we have resonant inductive coupling, then capacitive coupling, magnetodynamic coupling, then we have microwaves, and of course the light waves. So these are the different techniques. And then as you decide a particular technique, then you have the limitation in terms of frequency that you have to use, because when you are going to use the light waves or the microwaves, obviously you'll be operating in gigahertz to terahertz, and then these are different other frequency ranges. And then what are the associated devices or antennas you are going to use? Obviously these will be coils, most of these cases will be coils, but here you have the parabolic dish antennas, phased array antennas. In fact, some of the very important applications like energizing or powering a unmanned vehicles, a drone kind of thing, we can have the microwave beaming, and we can transfer the power, not maybe very far, but quite at least few hundred meters kind of thing, using this kind of far field wireless power transfer. So it has quite interesting applications. And then if you compare the different techniques that we have divided, that is the microwave to electromagnetic induction to magnetic resonance and other kind of circuit, other kind of concepts. And then if you just basically make a plot of wireless transmission range and transmitted power, then this plot actually and these shades actually indicates which one you have to apply for which kind of application. So when you are having you are working on the low power range, and then you can have a quite bit of transfer distance, 1 meter or to 10 meter, which is good enough for biomedical applications I was talking about, right? So we can deploy the microwave based transfer. But for MRI, medical resonance and stuff like that, efficiency is probably better, 40 to 60%, but you have to deal with a low transfer distance, and you are getting a little bit of more power, of course. And then with electromagnetic induction, you have a good amount of power bandwidth. You can have medium power to high power applications, but the transfer range is going to be very small because this is inductive coupling. Okay, so depending on the situation and depending on the frequency range and operation, you have to take a call and you have to deploy the proper technology. So this was the experiment I was mentioning, that at MIT labs, and then Professor Aronson sample. After that, many groups have tried to repeat this kind of experiment. probably seeing the size of some other things, you can try to guess the idea, I mean, how big these coils are. And this is working at a very low frequency range. It is at MIT in 2007. So this is inside the lab. You have a transmitter coil and you have a receiver coil, and you can transfer the power from one coil to another coil using this kind of concepts. And a new wing of research is retrodirective wireless power transfer. So in this retrodirective wireless power transfer, basically you have to transfer the power towards a certain direction, from which direction the power is coming from. That means you have a kind of pilot signal. So that pilot signal from, for example, I was mentioning about unmanned vehicles or the drone kind of application. So the pilot signal will have an omnidirectional antenna, and it will just send a power, and that your receiver has to receive that one. So that is the injection or triggering. After receiving the trigger signal, you have to transfer the power in the direction from which the signal came from. So this particular concept is basically the retrodirective concept. This is interesting animation from Wikipedia. As you can see that using different kind of techniques like corner reflectors or Van array and or phase conjugation technique, you can actually actuate this retrodirective concept. So these are the two topologies which people are employing for these retrodirective power transfer. One is the Van array configuration, and is the phase conjugate configuration. So this is a basic block diagram over here. As you can see that you have an incoming RF, and this incoming RF of course will have different phase front, and depending on the phase front, actually you have to adjust the phase differences over here, so that the different elements of the array are at different phases, and ultimately you have to make sure that this power is going in the direction from which the signal is coming from. Whereas in the phase conjugation technique, you can see this is you are applying a conjugate phase from your network, and thereby you are achieving the condition to transfer the power in that particular direction. You can go into the details of this few articles to have some more detailed idea regarding this particular thing. And this is the active configuration, where you have the combination of the phased array and the active devices together. Now this is the last doing of my talk, where I am going to discuss the dielectric resonator based WPT using SCR, which is the split cavity resonators. This is the work that we did at Royal Military College of Canada during 2017 and 2018 with Professor Yahya Antar and Dr. Same, who is from industry but also affiliated with Royal Military College of Canada. And during some of the experiment, we got some support from Professor Frondhofer also in terms of certain discussions. So this is a general schematic. The idea of complex system or the compound pendulum. Like we have a bob, simple harmonic oscillator. We have a bob which is actually oscillating in a particular fashion in its natural frequency. But when we have two bobs connected, then they have their own natural frequency. But due to the coupling, they have some other mode of oscillation also. So sometimes we call the symmetric mode or anti-symmetric mode of oscillation. So this type of concept is used over here to actuate a concept which is called EIT, electromagnetic induced transparency. So in our work, I'll be coming very soon. There are three kinds of resonators which are coupled. So resonator 1 and 3 are identical, which are basically the dielectric resonators, and the resonator 2, which is basically an intermediate medium. In our case, it is a split cavity resonator. So they are coupled by a coefficient of coupling K. And when you apply the coupled mode theory, you come up with this equation, and then you can come up with these eigenvalue equations. If you solve this particular equation, then you actually get three different frequency of oscillation. So they have their natural frequency of resonances. So this is an analogy of the same kind of thing. It is showing three resonators which are coupled, 1, 2, 3. Okay, so in our case, as I mentioned, 1 and 3 are basically dielectric resonators, quite a high Q, I can say. The material we used had an epsilon of close to 30. And then initially their resonances are same, but due to the coupling, there will be three modes excited. One is their natural mode, which is called the non-bonding mode. We call it plus plus minus mode. indicating that DR1 is and DR3 are 180-degree phase, phase deferred, whereas the second medium is in phase with respect to one of those DRs, and resulting a null component in the cavity mode. Then we have the bonding mode, which is basically plus 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 mode, and then anti-bonding mode, which is plus minus and minus mode. Interestingly, this non-bonding mode, at the non-bonding mode frequency, which is symmetrically placed between the bonding and anti-bonding mode, you can transfer the maximum amount of power. So as I mentioned, that we have a cavity resonator, split cavity resonator, intermediate system, which is medium 2 over here. And inside this cavity resonator, split cavity resonator, we have 2 dielectric resonators. So we have to think, how do we excite one of our DRs? Because one of our DRs are actually the transmitter, and the second DR is actually the receiver. So if you see the waveguide excitation technique, there are different ideas depending on which mode you want to excite. So one is the coupling through holes, then coupling through the probe. For example, if you want to excite the TE10 type of mode, you'll excite through these mechanisms, or you can go for coupling loop or other kind of ideas also. So this is the overall schematic taken from the simulator as far as our technique of wireless power transfer is concerned. As I mentioned, these are the 3 resonators. So this is a special split cavity resonator. It is designed in a way such that through this gap HFS, which is the distance between the two these two fins which is coming from here, there is not much radiation leakage. So these are the flanges. So we make sure this flange to flange distance is HFS, which we varied over some 7 to 10 centimeter kind of thing, and for certain frequency, and because this cavity, depending on this distance also, the cavity resonance frequency will be determined. So these DR's resonance and the cavity resonance initially are kept same, but when you solve this equation, as I mentioned, you get 3 different frequencies which are named as bonding, anti-bonding, and non-bonding mode. So, and then how do you excite these DRs? This is very interesting. As you can see, these are the dielectric resonators which are actually excited by TE01 del mode. I'll be showing those mode configuration very soon. So to excite the TE01 mode, the type of electric and magnetic field it has, we have to excite through a loop like this. So this is the excitation loop, and then the power goes through this cavity resonator, and this is the, you can say this is receiver, in the sense it is symmetric or reciprocal, you can say, because you can transmit from here and you can receive from here as well. So these are the excitation loops, and depending on the diameter of the dielectric resonators and this height of the GR, and of course its epsilon r, its resonance frequency of different modes will be decided. So we decided the TE01 dual mode, because with this mode the good coupling happens with the SCR TE011 and TE012 mode. So this performance of this system is characterized by transfer efficiency, robustness, or scalability, because we know we can't always keep this HFS constant. We have to have some variation with respect to this performance, considering intrinsic losses, because these losses of the cavity and losses associated with the dielectric resonators have to be considered, then impact due to unavoidable detuning. So this is some analysis as far as the different possible detunings are considered. So delta is one kind of error, you can say. So when you have delta non-zero, then you have the anti-bonding and the bonding mode frequency deferred by this equation, root 2k omega naught. Omega naught is the natural frequency and k is the coefficient of coupling. But in a symmetric condition, when you don't have any kind of error or any kind of deviation, you have anti-bonding and the bonding mode, which symmetrically placed with respect to the natural resonance, which is corresponding to the non-bonding mode. But for delta greater than 0 or delta less than 0, which corresponds to deliberate detuning, which is unavoidable, you are going to have the anti-bonding mode frequency intact, which is sorry, non-bonding mode, which is green line over here, is intact, but anti-bonding and bonding mode frequencies either moves up or moves down, depending on whether delta greater than 0 and delta less than 0. So this is a S parameter result of the overall setup. As you can see, these are indicating these 3 modes: the bonding mode, non-bonding mode, and the anti-bonding mode. And at this particular frequency, S21 close to 0 and S11, as you can see, it's the simulation result, but I'll show you the measured results also. This corresponds to a very good transfer efficiency. So there are more theoretical work was carried out in terms of transfer efficiency calculation theoretically using circuit simulator and then EN simulator, and of course the final measurement. I'll be showing some of those interesting results. But before that, let me talk about the ideas, like what is the basic philosophy, how do we decide the DR modes, how do you decide the SCR mode, and stuff like that. Then I'll show you the experimental results. Dr. Toimur, how many more minutes do I have?
Around 10 minutes you can take, no problem.
Okay, thank you. So as you can see, this is TE01 del mode. So as all of you are aware of that, this 0 is the azimuthal variation, the second subscript is basically the radial variation, and the third subscript is actually the height variation, I mean along the z-axis variation. So this is the top view on the dielectric resonators, and this is the side view. That's why it looks like a rectangle, but it's a cylinder, as you know. So in the TE01 del mode, this is the field configuration which is basically the electric field over here. And as you can see that it is azimuthally symmetric. It has a one variation between center to radius, and this del close to 1 over here, because this is the fundamental mode. And then we have hybrid modes, then we have TM mode, and then this is the second T01 del mode kind of thing. That is, this is T01, but the third substitute is 1 plus del mode. That's why you are almost getting 2 Haber plane variation along the z-axis, along the height of the dielectric resonator. So these two modes are having proper orientation with respect to the SCR mode. Why I am saying this? Because when the SCR, which is the split cavity resonators, which works like a closed cavity resonator as far as the design is concerned, because we make sure that the flange distance is such that it won't work as a radial waveguide, rather it will be almost similar to the conventional cavity mode. So when you see the results over here, the different modes, I mean, we using HFSS eigenmode solver, we did a lot of analysis. Of course, the theoretical part is there, but this is T011 mode. I have shown it in a red box over here. This mode and the DR mode, 01 del mode, are somewhat symmetric. And then T012 mode also will have similar kind of configuration, because the last two will be indicating another change along z-axis. So these two modes will have a very beautiful friendship. So these two modes are chosen for our excitation of the cavity as well as for the dielectric resonator. So this is the choices of the suitable cavity and DR modes, as I mentioned over here. So this is standalone DR, and this is the cavity. So there is a beautiful matching, and then using the theoretical analysis and closed form equations, so we calculated the resonance frequency of those DR modes, and we decided our frequency of operation. This is the different parameters. You can see the papers that has come out from this work to go into the details of this. And more interestingly, a lot of involved circuit modeling was done, because I am talking about different kind of resonators and their coupling, dielectric resonators, split cavity resonators, and so on and so forth. So the first figure over here is a circuit model of inductively coupled resonators for a overall general WPT system. But then using some circuit schematic and circuit topologies, you can actually simplify this particular circuit to come up to this particular circuit. And then, as I mentioned, there are 3 modes: the bonding mode, anti-bonding mode, and non-bonding mode. So the same concept, as you know, when you have a compound pendulum, depending on the type of excitation, you can have symmetric mode excited, which goes like this. You can have anti-symmetric mode excited, which goes like this, right? And if it oscillates in the natural frequency, then compound pendulum will oscillate as good as a standalone oscillator. I mean, without proper coupling between them, as if the third coupler or third coupling network is not there. So this, I mean, just try to give you a physical analogy. So they are called symmetric or anti-symmetric mode. So in the symmetric mode, this coupling, mutual coupling, and the anti-symmetric mode, this mutual coupling are in the opposite direction. And as far as the arc topology is concerned, so this is the source, which is basically from the experimental aspect. This goes from the one port of the VNA, and this is the load. This goes to the second port of the VNA, but in actual experiment, these will be going to a particular load. And these are the different frequencies corresponding to the non-bonding mode, which is the standalone resonance frequency. But when you have bonding or anti-bonding mode, your resonances, frequency is deviated, which is given by this. And this is a circuit topology, very interesting circuit topology, because these all the modes are available simultaneously. But interestingly, at non-bonding mode, where we have the EIT kind of scheme, we have the maximum power getting transferred from the source to the load. So this is discussed in very detail in our article, so you can go into more details of this. This involves actually a lot of calculation and lot of circuit analysis and stuff like that. So this is a EM simulation and parametric analysis. As I mentioned, that we have very different parameters to get detailed idea about the detuning effect. So these are some detuning effect in terms of the cavity radius, in terms of other parameters. So these are the three different modes I was talking about due to the EIT scheme. This one is our interest, non-bonding mode. In fact, time is a bit short, but I have very interesting animation. I'll try to show you maybe one of them. So as I mentioned, that in this particular mode, you can follow the arrow direction 1, 1, 1. So all are in the same direction. Okay, so this is the actually H field in ampere per meter. You can see probably its instantaneous direction, all as well as it is in the same direction. So it is ensuring a bonding type of mode. But at the other modes, as I mentioned, there will be different kind of coupling between the two dielectric resonators. So a very detailed study in terms of theoretical EM analysis and experimental work was done, and we have seen the system is quite robust with respect to because we have to consider of different fabrication error tolerances also coming into the picture. So we call it a detuning effect. Deliberate detuning might be there. So over a broad range of variation of RC, you see our efficiency is close to 90%. And then the work was repeated by embedding different kind of parasitic objects inside the two cavity in terms of woods, in terms of glass, and so on and so forth, to get an idea that the system works through when an extraneous object is also present over here. This might have some implications that through wall power transfer or through wall kind of sending some signals or stuff like that is applicable over here. So these two blue rectangles here are indicating some plastic objects or some wooden objects. So we considered the proper dielectric constant considering the different kind of materials. In fact, while doing the experiment also, we repeated the concept. So these are the fabricated prototypes. I'm very thankful to the some of the mechanical engineers or the mechanics who spent a lot of time in coming up with this kind of structures, because it was quite complicated, and using this kind of aluminum foil and this copper tape, these two halves of the split cavities are designed, and we spent quite a lot of time in the lab, which is just in front of the RMC anechoic chamber, and then using this kind of improvisation by putting these some kind of foams and then putting some kind of holes to support the dielectric resonators. As you can see, for exciting the dielectric resonators, we have the loops, as I indicated in my simulation diagram earlier. So through these loops, this DR is going to be excited, and second piece sits over there. And in this particular experiment, probably you can see there is a piece of plastic which was like almost half an inch thick. With these also, the experiment was done, and the result was quite interesting. So these are some experimental picture. As I indicated through the theory, the coupled mode theory, that there are three modes. So you can clearly see the three modes. And this actually the yellow one is screenshot of the VNA. The yellow one is indicating the S21 almost close to 0 dB, and S1 on going close to minus 20 dB. This indicates a good transfer efficiency. And later on, we did a lot of post processing to come up with efficiency plot, with theory, with our simulation, with our measurement, and the result was quite interesting. Probably I'm taking a bit of more time, so I'll go fasting. Very fast. So this is the with and without SCR mode. The experiment was repeated, and we can see that with different combinations, the figure of merit analysis and stuff like that, the result is very consistent, and we got efficiency above 70% in most of the cases. And this is the extension of the work currently we are doing. I'll not go into the details of that. Currently we are applying these concepts to exhibit or to demonstrate power, wireless power through aqueous medium. So suppose some swimming pools or some kind of this as other implication in terms of biomedical applications, because we know it's not an aqueous medium, but there are a lot of complicated thing over here. So in this particular experiment, we are considering same idea, but this is a dielectric medium, and then we have very high Q dielectric resonators in presence of different conducting objects or air bubbles and stuff like that. So similar kind of approach currently is on, and this indicates the modes I talked about, that is the bonding, anti-bonding, and non-bonding modes and associated resonance frequency. And this is the eigenspace diagram. So currently more work is under progress on this particular fonts. So for getting more details as far as our work is concerned, which was the second half of my talk, you please feel free to write to me if you have any queries, and you can go into the details of these 3 articles. The first 2 are at WPTC Montreal, IEEE Wireless Power Transfer Conference, MTTS conference it is, and this is recently published in Journal of Applied Physics, and something more are in pipeline. So with this, I conclude my talk. My thanks to all the collaborators, all the agencies, Professor Yahya Antar, my collaborators, Dr. Same, Dr. Siddiqui, and some of those things, not directly but indirectly. IEEE also has been very helpful in some of the things, especially for attending conferences, doing some leadership activities also, and then ISRO also. So these are the people who have been directly involved in this particular kind of work. Incidentally, when I was in this experimental part was repeated quite a few times, 2-3 times. Incidentally, Professor Siddiqui was also present during the one of those measurements happening. And these, as everyone know, the first figure is Professor Anta, and this is Dr. Same, who was very much involved. So these are some of the students who have worked with me. So with this, I conclude my talk. Thank you very much. And the first part I was showing has recently come up in terms of a book, which is authored by Professor Antar, Dr. Siddiqui, and myself, with Taylor and Francis. Thank you very much.
Thank you, Professor Saha, for covering different aspects related to energy harvesting as well as wireless power transfer. Now, as far as query is concerned, the first query on your talk is, any technique is there for wideband and ultra wideband matching network? Is there any technique for designing wideband and ultra wideband matching techniques or some?
Yeah. So yeah, it's a very interesting question. In fact, that part of the harvesting is the most challenging part. So for harvesting, wideband harvesting, the main challenge will not be from the antenna fronts. The main challenge will be on the matching front. So we have to go for different kind of tapered matching, or some Kleffenstein matching, or some other kind of improvised matching to enhance that particular matching bandwidth.
Okay. The second query is, what's the criteria for selecting rectify elements for REHS and WPT applications? Rectifying elements means both, like rectifier diodes, FET, MOSFET, or some other active elements. What are the criteria for selecting them?
Yeah, it's again a very good question, I would say. One of the thing is, of course, your frequency of operation, and the other thing is you have different topologies. I mean, I don't know what he's exactly meaning by elements. Probably he's talking about the topologies, like whether he wants the series or shunt type of thing. As I was discussing in some of the slides, it depends on the power level actually. So if I am working on the low power level or high power level, depending on that, I can go for shunt topology or series topology or some mixed topology kind of thing.
Okay, thank you. Now, next query is, could you please explore some applications of near field WPT in real life?
Yeah, the some of the applications we are also looking for. Many people are looking ahead on that particular thing. Is the biomedical applications to energize some of the biomedical gadgets. So that would be very, very interesting, because their power requirement is also very low. So in our experiment, as I was showing at the fag end of my presentation, we are deliberately loading the cavity by some kind of extraneous object in terms of wooden block or something like that. But as a very basic time, try to reduce the sizes of this cavity also later on by different kind of loading, and thereby we can probably show that it will have some real applications in terms of the near field applications also, because here the transfer distance is pretty low, and it is in terms of lambda, if I say, it is kind of like some lambda by 2 to a few lambdas only.
Okay. The last query on your talk is, out of printed antennas and dielectric resonator antenna, which would you prefer for biomedical or implantable devices?
Dielectric resonators, because of its non-conformality, probably will not be a great choice for implanted devices. Some of my students currently are doing some antennas for endoscopy kind of applications. So there we are going for printed antennas. But for dielectric resonators, we'll have better applications because it has a high quality factor for harvesting kind of applications.
Okay. With this, I thank you once again, Professor Shah, for your wonderful talk, as well as nicely handling all the queries, most of the queries raised by the participants. Thank you, Professor Saha, once again. Now, in the queue, our next speaker is there, Professor KJ Vinoy. Professor
Thank
KJ
you
Vinoy.
very much. Thank you, Dr. Toimur, for this opportunity, and we look forward to collaborate with you and work with you in future. And all the best for all the next portions of this beautiful workshop, which is going really nice. Thank you very much.
Thank you very much. Professor KJ Vinoy, Dr. Chinmay Shah, you please block your presentation.
Yeah, I have stopped sharing.
Okay.
Probably getting muted as well. Are you present on now? I think so.
Is this screen visible to all of you?
Yeah.
Yes,
okay.
I can see your slide now.
Okay. It is my immense pleasure and gratitude to welcome the next distinguished speaker of second day session, Dr. KJ Vinoy, Professor, Indian Institute of Science, Bangalore, India. KJ Vinoy obtained PhD degree from Pennsylvania State University, USA in 2002. Earlier, he obtained MTech in Electronics from Cochin University of Science and Technology, Kochi, and BTech in Applied Electronics and Instrumentation from College of Engineering, Trivandrum. He worked at the National Aerospace Laboratory, Bangalore, India from 1994 to 98. After his PhD, he joined the Indian Institute of Science, Bangalore, as an assistant professor in 2003, where he is currently a professor at the Electrical Communication Engineering Department. Additionally, he is also serving as the chairperson of the Center for Scientific and Industrial Consultancy and the Office of Career Counseling and Placement at ISC Bangalore. His research interests cover several aspects of RF and microwave engineering, including microwave and millimeter wave antennas, microwave circuits, microwave-based sensing and imaging, and computational electromagnetics. His doctoral research on fractal-shaped antennas is widely cited. He has co-authored 5 books and over 90 research articles published in reputed journals. As part of an ongoing project on indigenous 5G testbed development activity, he has demonstrated a beam steering antenna array at 26 GHz band for the Indian requirement. He holds 2 US patents and has filed 3 other patents in India. He was awarded Only Cell Rode Innovative Conference Paper Award on Computational Electromagnetics in 2015. He has been elected as Fellow of Indian National Academy of Engineering INAE in 2011. With this, I welcome you and invite you, Professor Vinoy, for this workshop, and please start your talk. Am I audible, Professor Vinoy?
Yes, I'll just share my
Oh, okay.
computer now. Can you see my screen now?
Yeah, it is coming.
Can I start? Is it there? Has it come?
Yeah.
Am I audible?
Yes, you are audible.
Okay. And the screen is also there, right?
Yeah. Uh,
Okay. Good. Can I go? Dr. Taimur, can I get started?
yes, please carry on.
Okay, fine. Hello, welcome to everybody from different parts of the country.
Professor Vinoy, your volume is too low. You please bring your microphone near to your mouth.
Okay. Is it better now?
Yeah.
Is it better now?
It is fine now.
Okay. Okay, fine. Good. So once again, welcome to this talk, the second day, the second talk on powering of Internet of Things from RF. So I'm the Indian Institute of Science in Bangalore, as it was introduced. The Indian Institute of Science, but I'm in the ECE department here, which has a vision of excellence in theoretical and experimental research, especially in areas of communication, signal processing, microelectronics, RF and photonics. We have about 25 faculty and 2 more are joining in the next few weeks. And with many of them, fellows of different academies in India and also fellows of IEEE. And we are all active in publishing books, book chapters, journal references, and various such professional activities. And much of the research that is happening here is collaborative in nature, as you could see from the set of pictures that I share with you. It could vary from devices level, or when to some extent some kind of materials like film or nanomaterials going into nano electronic devices, to signal processing, to VLSI design, to optics, to implementation of sensors in realistic environments. In one research group, we primarily focus on some aspects of microwave engineering. If I cover some of the topics that my students, PhD students particularly, has worked on in recent years, one of my recent PhD students worked on RF MEMS switch, where we are trying to design devices which work at a very low actuation voltage and having a very good yield as well as reliability for continuous operation. We were test device for 10 million cycles, and for want of time, we sort of discontinued because the test, because there was no change observed in those. Earlier on, another of my students worked on a what we call as a mesoscale phase shifter based phased array antenna on a board. So in here, all the entire device is actually assembled on a regular printed circuit board, so that the entire antenna is assembled there, rather than building a phase shifter separately and integrating it over to a phased array module. As it was mentioned before, we also work on computational techniques, particularly using finite element method-based solvers. And one of the emphasis recently has been to look at efficient ways of quantifying uncertainties due to fabrication. And some of the effects that we are trying to model these days include changes in dielectric constant, or changes in conductivity, or in some instances changes in dimension that are very prevalent, especially at high frequencies. For example, as we take into consideration designs running into terahertz and that kind of frequencies. On another aspect, we are also trying to see if we can build low power radar systems that could probably be used as some kind of network radars in a city scale development. The work in this direction is at a very nascent stage, and hopefully we'll have something to report maybe in the next few months or years. Another area that we are currently looking at is beam steering antennas, and as you see here, we are in the process of building a array of antenna which is working at 26 gigahertz for 5G millimeter wave communication kind of applications. Now let's come to the topic. In this particular talk, I want to cover briefly about wireless power transfer and RF energy harvesting, and how these could be used to power real Internet of Things devices, where you have all aspects of the remote device being covered. In that context, I will cover the work of some of my MTech students over the last, let's say, 10 years or so. And we will cover some of the realities, some of the issues that we have faced in trying to, and I'll essentially address some of the case studies that they have done in trying to basically harvest energy out of cellular tower radiations, or harvesting out of the radiations from your own phone. And we also have worked on integrating sensors with a commercial RFID chip. And on the other side, we also worked on building a chip of our own with which we could do the power conversion, so that a microcontroller could be energized using the signal or the energy that we accumulate. And as I said, I will cover some of the key challenges that we were trying to address in each of these projects. Recently, we also worked on harvesting energy from FM radio bands to, show some interesting possibility of using this energy to, structural health monitoring as a typical example. Last case study that I will present is actually a near field charging experiment that we tried at 2.4 gigahertz, and in such a way that we might be, it might be possible to charge wearable devices without actually locking it onto a charging pad kind of an environment. So let me start with the wireless, a brief introduction of wireless power transfer. Dr. Chinmay Saha has given a fairly elaborate historical background. So I'll basically quickly run through the slides that I have in this direction. It essentially tries, yes. I am almost touching there. So I guess this is the best I could get. Yeah, yeah, okay. All right. So in wireless power transfer, what we try to do is essentially transfer the electric energy remotely. And this, as Dr. Saha has mentioned, has a very long history, all the way back to the times of Tesla. But it actually picked up steam in 1960s, as he was showing in one of the charts, when a scientist by name Dr. Brown has actually shown run some experiments, and he has actually shown that he could transfer power to a helicopter from the ground. And he actually was the one who coined the term rectenna that many of us use these days in the context of wireless power transfer or energy harvesting. So one interesting aspect here is that these demonstrations actually involved, a dedicated source with fairly large power, so that what is being transmitted and received at the end will have reasonably, a good, reasonable power to use something for. My own personal exposure to this area happened in late 1990s, when actually my PhD supervisor at that time was interested in this topic because there were several funding opportunities that was coming up those days from Japan, where they were actually trying to see if space solar power satellites could be deployed to power their islands remotely, in the night, because the satellites could still be collecting solar radiations, and if there are some ways in which you can beam the energy at micro frequencies down to Earth. And we were actually working on a proposal jointly with several other universities those days. The area, as again, one as Dr. Saha mentioned, this area picked steam in mid early 2000s, when in the MIT experiment, where they actually showed that a substantial amount of power can be transferred over reasonable distances, 1 to 2 meters, at relatively low frequencies for us. And but they were able to show that energy transfer is possible at fairly high efficiencies. And soon, there were industry standards with which wirelessly charging devices and other things that came to force. So if you actually compare these last two examples, there are several interesting connections between them. Of course, the free space loss factor is a major bottleneck when it comes to transferring power from space to Earth. And these short or near field demonstrations that were shown at MIT, or these standard that I just mentioned, they are really practical examples of how we could use wireless power transfer for exciting use. So these two are, in fact, two different extremes of, I would say, wireless power transfer in terms of the power itself, whether one of them could be of the range of milliwatts, whereas the other one, the target is of the order of megawatt. And, the distances are hugely different. So are the frequencies, and the size of the objects that we are talking about are also potentially going to be hugely different. And of course, one of them is commercial, as you all know. The other remains a blue sky research, even as of date. So the focus of our talk is essentially, the far-field transfer of RF energy, and what it involves essentially are, the antenna and the matching circuit, as Dr. Saha mentioned, and a rectifying diode, and subsequently there could be other components which are also of serious importance. From RF microwave perspective, we focus on and the antenna and the matching circuit that follow there. But there are several other aspects to this story. If you want to actually try to energize a device to do a wireless communication, we may have to store this energy in batteries. So we need to, there could be serious research required to store energy with high efficiency over long durations. We need to, there are interesting challenges in designing power management circuits, which by themselves do not consume so much of power, but at the same time work at potentially at very low voltages and can be started with the low energy that is actually available. And Another aspect of this whole scheme of things could be efficient communication protocols with which these devices could be maintained over long periods of time and still be able to, one should be able to communicate from these devices and collect the data and other things as we move on. Now, let me briefly touch upon what we could potentially be, meaning when we say Internet of Things. And one of the ways in which we could explain this is by comparing this to, radio frequency identification tags and similar devices. And the reason will be obvious in a second. In the case of RFID uh, system, what we have is a reader antenna, which is connected to a reader unit, and we may have a computing system that supports it. On the other hand, what is deployed is actually a tag, which is usually a very small device and which may have a extremely small integrated circuit in it, which actually help the reader identify the unique ID of the package by which is actually encoded into the IC that is there in the tag, and the tag itself is pasted onto the package that you see here. This communication scheme is very efficient in many respects, and this efficiency is forced because the tags are expected to be extremely cheap devices, which can be attached to all these disposable packages, let us say. Whereas on the other hand, the communication and most of the overhead in the communication is taken actually by the reader. In fact, much of the work is done by the reader. The tag is almost passive, and you, as I said, you have a very small integrated circuit which does very little functions. Now, how is this integrated circuit powered? This is actually powered by the tag itself. So, this follows what is called a backscatter communication, wherein the signals coming from the tag itself is used to modulate by some kind of impedance modulation, and that when it is scattered back into the reader, the identification code for the device is embedded into it, so that the reader will be able to identify the device number by analyzing the echo that is coming from through the backscatter. So uh, there are several interesting aspects in this particular device that you see here in the RFID, which is here we are using radio frequency waves for identifying or simply tracking this object. And it is obviously the why I took that example is that it is proven to be a very simple and a cost-effective solution for the entire scheme of things. And these tags it's very cheap, and it is possible to be attached on almost any everyday object that you have there. So in many respects, RFID is considered a prerequisite, and what many people tried to do was essentially augment the capability of an RFID tag to bring in various other aspects that you would need, that you would expect in Internet of Things. And some of the common examples of the sensors working on energy harvesting system were actually augmented versions of RFID, where the sensed information is piggybacking on the sensing, the ID sensing information. So essentially, it is a slightly modified tag in which the sensed information is passed back by the ID chip into towards the reader, and the reader will be able to sense this information. One of the case studies that we have done is in this direction, and I will talk about it as we move on. Now, if you As I mentioned before, the Internet of Things could be thought of as an extended version of RFID in the sense that we bring in sensors, we will bring in several other smart technologies or nanotechnologies to form, Internet of Things. So in a shop scenario where you would use the RFID to actually, get the package, the unique number of a package. Whereas in this case, we could be using it to, identify the goods, the quality of the goods, or maybe, it could be in terms of opening doors, it could be automatic scanners, it could be many, many other functions could be done by integrating, some of these additional features into RFID. And it was sort of speculated, I would say, that a lot of day-to-day activities could be seriously influenced by Internet of Things or cyber physical systems in general, and one should be able to get into this. And one of the major bottlenecks of deploying this technology is how we could, power these devices when these are in billions of devices deployed all around us. And one of the solutions that were looked at was actually to power them using by energy harvesting. And again, one of the schemes for doing it is actually by uh, powering with RF energy, either by power transfer or by harvesting. So, if we really compare Internet of Things with what is there today in ICT, in a typical ICT system, we could we could say it connects devices anytime, any place with for anyone. But with all these three A's, we add another A, which is anything in when it comes to IoT. So in this scheme of connecting things, we may have sensors, actuators, and many other smart technologies. These enable, more than person to person. It's more like object to object communication could be possible, and it would involve therefore sensing, communication, and control, and also looking at technologies for power at the kind of scale that we are looking at. And obviously, continuous availability of power is crucial for deploying this kind of a large number of devices, for Internet of Things applications as it is envisaged. So now, if you really look at some of the sensors that one could use and their, consumption, there could be, we may need temperature sensors, humidity sensors, pressure sensors, which are used in a large number of applications, or it could be strain gauges. And if you look at the current consumption, this could range from a fraction of microamperes to thousands of microamperes or milliamperes. And we may have some flexibility in the supply voltage that would be required. Now, when it comes to communication, wireless protocols in general, if you look at 2.4 gigahertz ISM band itself, there are several technologies one may be using. It could be Bluetooth low energy on one end to wireless LAN on the other end. We may have, all these decisions could be based on the power requirements, the data rate requirements, and and the kind of battery life support that the technology can provide, or how, as I mentioned about the energy harvesting protocols, how these could be employed in some of those is could be another reason how one may choose the communication technology per se. Now, the power requirements perspective, if you really look through the power requirements for a set of devices that one may want to energize, it may range from smartphones, which may require watts of power, to small devices like a small wristwatch, which may run on microwatts of power. and the like. So there is, as you could see, several orders of magnitude difference in power in requirement in many of these devices. I mentioned about wristwatch by intentionally. If you may recall, some of you may recall that we used to have what are called automatic watches, which did not require winding or battery at some time back. These actually work by mechanical harvesting of energy. So now what we are talking about in this particular event, we are primarily targeting harvesting of energy using radio frequency radiations. So in this chart, as you could see, there is 6 orders of magnitude variation in the requirement for communication system itself. So in general, what we require is actually a wireless sensor node. In some sense, I typically say that Internet of Things is a glorified name for wireless sensor network. That it was there 20 years ago, and nowadays people talk of it in terms of as Internet of Things in general. Now, if you really look at the demand and supply for the energy that we are talking about, for communication to happen, we may actually need a large current to be drawn by the transmitter. So one way to basically do this is by buffering or accumulating energy for over a period of time and then drive the communication. It could be done using rechargeable batteries in the form, for example, of thin film batteries, which have become very popular in many of these kind of schemes. These can be, very flexible and can be integrated with plastics and other convenient foams. There are also an approach called supercapacitors, which where unfortunately there used to be serious leakage issues, especially when you actually store energy in them at very low voltages. Why I mention this is that when you design a system to store the energy, we need to be concerned about and aware of the limitations of existing technologies. And there are several challenges in these technologies, especially when you try to, energize them at very low voltages. So this is a quick comparison of some of the battery technologies and supercapacitors. One of the main advantages of supercapacitors is that this could be run through tens of thousands of charging cycles, and therefore is considered to be very useful in the context of Internet of Things, and where you can actually use it for a very long periods of time. Um, uh, Let me just continue. There are also approaches where we could actually use, we could say that these are, in some sense, battery-less wireless terminals, in the sense that, you don't store the energy for a very long period of operation. Rather, we store sufficient energy just for keeping the communication node intact. So most of our work is actually towards having a battery less terminal. When I say battery less, it does not mean that there is no storage of energy. There will be some storage of energy, but essentially you just survive with the minimum energy that is required. And we try to do the communication. We try to design the communication protocol in such a way that we'll be able to do the communication with this kind of minimum energy that we can accumulate. These are particularly useful when these terminals could potentially be embedded within structures, which could be mean that civil structures, or in some rare instances, it may even be possible to embed these within the body. These devices could even be deployed in very hostile environments. Uh, when I say hostile, it's like areas where human cannot get in and change the battery. For example, in some sense, in a kind of like a nuclear environment and things like that. Or there are situations where a battery is not allowed at all. For example, one of the projects that we worked on was actually to see if a RFID tag sensor could be employed within the fuel tank of an aircraft itself. Of course, there could be other factors such as cost and weight. This was a survey that we did several years ago, where we tried to look at some of the commercially or otherwise available technologies for wirelessly powered communication terminals. And what you see here is actually one of the demonstrations from University of Washington. I will talk about it in the next slide. And there are there are tag-based technologies. There are chips which came from a company called Spartacus, and there are also university solutions where chipless RFID based energy harvester devices were also available. And there are several others which came along in the years later. So this was one of the technologies that were available at the time when we actually started our work. And this is from the University of Washington, where actually they were trying to uh, enhance the capability of a RFID reader by including the sensed information. And for doing this, they have done very neat engineering, as you see here, of attaching the power energy management circuit at the base of the RFID antenna. And they had demonstrated the operation of this sensing device as a platform which could do multiple sensing functions. Uh, there was also a product available from a commercially available company called Powercast, which is actually one of the companies which has ICs that could be used for energy harvesting. So here again, but only aspect here is that these ICs work at relatively high power, and therefore from a energy harvesting point of view, if you try to employ them, the efficiency that you get was extremely poor. So so there are other suppliers also came along in recent years. But before we get into those, let's also look at what is the kind of power density that is available from various harvesting environments. I think Professor Alphonse mentioned about it yesterday in one of his talks. So we had explored some of these in various projects that we did in the recent years. As it was mentioned, the ambient RF, that is more like signals coming out from cellular towers and the like, are very small power density, that as we could see here. On the other hand, one could get substantially higher power using mechanical generators and the like. The uh, Therefore, it is not easy or convenient or maybe feasible at all to to work with a conventional sensor network just by using a RF or some of those kind of harvesting alone. We may need some kind of a backup arrangement with which you could do this. Now, one of the comparisons that is often made is how good is it compared to solar energy. Photovoltaic of course, is a very good source of energy, and you can get substantially higher, power density available by ambient light. In fact, in one of our work, we actually tried to do compare what kind of RF energy will produce a similar power at the other side, so that we can drive circuits. And we compared it, and we found a particular value for the RF incoming RF energy, which matches a typical lab lighting environment. So RF becomes a particularly interesting requirement, let us say, at night, of course, because there is no light available from outside. And also, some specialized scenarios where you are inside a closed chamber or a mine, or a tunnel, or some such situations. Um, in Unlike some of the other scenarios, you can have RF form of energy, either ambient, as it is for the cellular radiations, or it could be intentional, which is like you are actually directing the RF energy towards the sensing node. The ambient sources, as I mentioned here, could be base stations, or even the access points, or even your own mobile device. And some of the intentional sources could mean even RFID readers, some special beacons, or even charger devices. So now, if you look through what are the sources for harvesting, we may have Wi-Fi access points. Almost every room has it these days, especially in an industrial or an academic environment. Cellular towers radiate substantially higher power at 900 megahertz. You may have TV broadcast stations which broadcast at even higher power. You may have FM broadcast stations, or even AM radios which are there. Once we try to do this experiment, trying to see how much is the power that you can measure in spectrum analyzer in my own office, for example. And we found that the maximum power that we see is actually at the FM broadcast bands. And these, obviously, all these technologies are at different frequencies, and therefore come with their advantages and disadvantages. And we have to essentially live with this and make our system efficient and practical at the kind of power levels, at the kind of frequency, obviously, and with the kind of availability of resources at that point. So a communication system typically will have a transmitter, an antenna, and on the other side you have a receiver, you have an antenna, and there is a channel in between. And this channel, obviously, with antenna engineers, all of them know that there is something called a free space loss. Let's look at it. What is it all about? When an antenna radiates, there is energy going, if you consider an isotropic radiator, the energy going in all directions, the net power is divided, and therefore the radiation intensity could be defined. And we can use that to find the directivity of an antenna. So the directivity of an antenna is how better or how good the radiator is compared to an isotropic radiator. Now we can use this concept to actually find the power received by an antenna, and there is this concept of 4 pi A by lambda square for comparing the directivity to the effective aperture of an antenna at a given wavelength. And these are essentially used in the Friis transmission equations to come up with the power transfer between the transmitter and the receiver. And it turns out that you have this expression which is involving the gains of the transmitter and the receiver, and you also have this term which is actually called the free space loss factor, which is lambda by 4 pi r the whole square. So, what is the impact of it? If you really try to see in wireless power transfer, this essentially forms the main bottleneck. And if you run through some of these numbers, you could see that even for a distance of 1 meter, the efficiency would drop down to something like 0.06%. So, even if you transmit several watts of power, which is probably what is possible because of health concerns and other factors, the power that you can actually receive in tens of meters come down to microwatts. So essentially, if you are trying to harvest the energy, we should be looking at the power levels, which is extremely small. As you see it, it is of the order of minus 20 to minus 30 dBm is the actual power that you can practically be collecting. So in our research, when we started, we tried to see what best we could do when we are exposed to this kind of extremely low radiations, and is it at all possible to harvest energy and do something useful with that? Are there other ways of energizing, and how we can control, how we can manage the power and integrate it with sensors? I was lucky to have some very bright students when we started this, and they were able to demonstrate the working of devices in this particular direction. So one of the key aspects here is actually the design of rectifier. And I'm sure all of you who are listening to me would have studied about it in the early days of your engineering. So what we need is not very different in functional terms with the rectifier that you would have studied, whether you must have studied about half-wave rectifiers and full-wave rectifiers. The only difference I may say, is actually in terms of the load that you have, because we may want to store the energy, and since the energy is being stored, the load is actually a capacitive load. And that introduces additional constraints for us, because we are now talking about connecting an antenna on the left hand side here to this diode network, and what the load on the other side of the diode is actually a capacitor. And how do we connect an antenna which we conventionally design for 50 ohms to a purely capacitive load? Obviously you will have a serious mismatch, impedance mismatch happening there. Now, another constraint there is that the power level that is available, as we just saw, is of the order of minus, 20 dBm, or as we said, in microwatts. So obviously, the voltage that comes at the input terminals of the diode is so small that even if the diode has a very small threshold voltage, hardly anything will cross the diode and reach the capacitor to be stored there. So, what can be done in that direction? What can be done is actually comes from the theory of matching circuits. And that is why matching circuit is extremely important in the context of, energy harvesting. This is typically a reactive circuit which has a quality factor. Now, if you work through the simple calculations for this, you can show that the voltage we see in the input terminals of the diode is actually the quality factor times the input voltage that you would have from the generator here. And in our context, that generator is your antenna. So if you have a high quality factor matching circuit, we will be able to boost the voltage and therefore cross the threshold of the diode. And that is, contrary to the antenna design concepts that we normally do. We would try to have, very high bandwidth antennas and circuits, whereas as you see here, here we need extremely high quality factor or as high as possible with the technologies that are available to us, so that we will be able to have higher voltage given the low input voltage that you may have um, from the antenna. So we could you have inductors and capacitors forming these matching circuits. This could be L section, pi section, T section, all kinds of possibilities exist. And as you could see here, there could be, frequency sensitivity for a given input power. The voltage that you can, the steady state voltage that you can get across the capacitor would, therefore be seriously frequency dependent. This is some experiment that we have done in our lab by giving in RF as the input power. So as you could see, even the rectification efficiency would be dropping as you move away from the power, away from the frequency and the like. So here is a typical performance from a rectifier that we had built at that time. And as you could see, it is, there is substantial difference in the voltage that you can generate across the capacitor based on the input power for obvious reasons. And you could see that the input, the matching condition also would change with frequency because of the power characteristics, nonlinear, so large signal characteristics of the diode. You could also see that the efficiency that you can get will be, dependent again on the power that you supply. So with all these constraints, this batch of students in my first batch of students to work on this problem, were able to build a multi-stage voltage power converter circuit with which you could actually power a wireless sensor terminal from the energy that was available from a mobile tower. So when I said multi-stage, what I meant was that the trickling energy that is coming because of the extremely low RF signal that is coming through the antenna is first stored in a supercapacitor. And as I mentioned before, the supercapacitors are poor if these have very low efficiency at low voltages. So we basically would want to maximize the voltage at the supercapacitor for a given time. So therefore, the management power management circuit on the other side of the capacitor should actually be ensuring that the minimum voltage across the supercapacitor does not go below certain value. And then we used DC-DC converters, and which also has another low leakage capacitor, because as I said, the supercapacitor is not a low leakage capacitor. So here we used a very highly efficient capacitors on the second stage. And then we had one more power management circuit through which we were able to drive typical CMOS microcontrollers with which the communication was done. So the entire circuit that you see here, except for the antenna that is used for accumulating the incoming RF energy, are all built into this small board. As you see here, you can probably it is almost like the size of your palm, and which has all these components. And we actually were able to harvest the energy coming from this tower that you see here. It was probably about 150 or 200 meters away. And what you see here as this plate here is actually the antenna that was used. It's a typical antenna for 900 megahertz, obviously. And what you see on the other side is this small antenna which is used to communicate to a laptop sensed signal. And what you is demonstrated here is actually that you're building up 3 plus volt here in a multimeter that you see here. In a lab environment, you can do even more serious tests in terms of how the efficiency of the circuit, the voltage that is built, and even we can do communication. And as I mentioned, these devices communicate very intermittently, because only the power management circuit in here was built in such a way that we will be able to it will turn on the wireless node only when it has sufficient energy to actually do a communication. So therefore, that was one of our benchmarks in terms of the performance of the device at different power levels. And as you could see from the last row of the table here, the it could vary from once in 2 minutes to once in 10 minutes, depending on the incoming power through collected through a diode a dipole antenna in this particular example here. We have actually tried to make several modifications to uh, the rectifying circuit by subsequent sets of students. And in one of those instances, we actually tried to compare how, at um, what RF power level you are almost matching the performance of indoor lighting that you have in the lab. And as you could see, the duty cycle of operation, which I just mentioned as one of our benchmarks for communication, was 20 seconds in the light intensity of 200 lux, which appears to be the a normal lighting with multiple tube lights in a lab. And and we can get that kind of a rate when you actually have something equivalent of minus 7 dBm, which is obviously not possible in a energy harvesting environment. You need substantially higher power to be available to get that power level. So one of the ways in which we could potentially get that much of RF power available is when you have a source, RF source close by. And one of the examples that we tried at that stage was actually your own phone. If you, for example, if you call someone and if your phone is in the talk mode, then the radiations that it emits could be used to harvest energy. Obviously, it is not a convenient way of transferring power, but we could see that it happens. But a more practical scenario could be one example that I started out with, which is an RFID tag integrated with a sensor. What it could involve is, once again, we could have a harvesting antenna wherein you may run through the same steps of RF to DC conversion and some kind of power regulation circuitry, which will drive a microcontroller, which essentially interfaces the sensed signal into an RFID chip. In the example that we actually tried some years ago, we used a Monza IC for the RFID tag. So essentially, these are the different components that you see there. On the left is actually the antenna that was used for harvesting, and in the middle is this antenna which we designed for the tag. These were designed by us in some sense, and what you see here is actually the tag IC, which is obviously a very small IC. On the other hand, the power circuitry that we could build during the time of an MTech student is obviously a fairly large, a comparatively large electronics, large area electronics. And it has all these parts for RF to DC conversion, and this DC to DC voltage and voltage magnification and switching, and obviously the data processing circuitry with which you could transfer the data and store it into the storage parts of the registers of the RFID chip. And we actually this student actually demonstrated it by powering using the RFID reader that you could see that you can see kept at I think 4 meters away. In this particular example, he was able to show even up to 7 meters away. And what you see here is in one case, in one modification of the previous circuit in which he used actually the same antenna for both for harvesting as well as for the communication aspect. If you really look through the numbers and find out the efficiency of the conversion from RF to DC to to do this useful work is extremely small. But of course, you have a practical application where you don't necessarily need to store energy, you don't need to have batteries. As long as the electronics last, the circuit would be able to send the sensed data or along with the sensed information. So around this time, we were also approached by one of the aircraft companies to look at, whether we can have an antenna designed particularly for um, sensing inside a fuel tank. So our focus in this particular work was actually to have a compact antenna uh, for this application. So the specifications were that we work on a 900 megahertz band with some size constraints, and obviously they wanted to work on FR4 because apparently that is one material which is resistant to the aircraft fuel kind of environment, proven to be resistant to that. So the main challenge that it turned out that we have an uncertainty with regard to the presence of fuel around this antenna. So our early design was something like this. We had a PFA antenna, something like what you see here inside. It is like an inverted F shape patch antenna with a foam spacer. And what we tried to do in the initial experiments was actually to put it inside a, let's say, a lunch box. And we did some experiments by dipping it inside a bucket of kerosene, which incidentally has the same or very close Daltic constant as the aircraft fuel. So the challenge here was actually to make sure that the operating frequency of the antenna is not detuned by the presence of the fuel, or it should work independent of how much deep the antenna is kept. Sorry. In fact, once we designed this antenna and this arrangement, the colleagues from the company were able to actually do some experiments using that, and they were able to do the power transfer and sensing experiment with that. We did some modifications to this antenna, again using some modified versions of planar, what they call as inverted F antenna. Once again, to ensure that what we tried to do was the antenna has sufficient bandwidth in this case at 900 megahertz, so that in the detuning that would happen because of the loading of the dielectric loading, because of the fuel that is there, you may still have ensure that the antenna is the operational and the power transfer does take place. So the another effort that we did in subsequent years was actually trying to see if we can build ASICs for the power management. And as you saw in a couple of slides back, the ASIC or the electronics that is required for the management of power was taking a large area. So we tried to come up with an interesting three-chip solution. One of the chips is actually for the harvesting part. Another would do the power management, and the third would work on sorry, the first one would do the harvesting and a little bit of power management, or rather the first phase of power management. A second IC will do a more elaborate control and management circuits, and a third communication IC, which will be a commercial IC. That's what our plan was. And with that, this one of the examples that we have done, as you could see here, this is the antenna with which you collect the energy, and this is the matching circuit. This was one of the early prototypes. So actually the IC was put on a carrier base here, and these were some of the other circuits required for the other parts of the circuit. And as you could see, the efficiency of power conversion is obviously very small because of the power levels that is available. So we try to modify this and try to work on a band where there is somewhat more power available. And as I have mentioned before, FM radio happens to be one of those opportunities that we had identified, especially in our own labs here. So we try to modify this particular circuit to see if we can actually, harvest energy out of the FM bands. And we try to do something more than that. We try to see if we can have a modular arrangement where we use FM as obviously one of these opportunities. We also try to include the a power transfer arrangement using the RFID reader kind of as a source for the energy. So essentially, it is a intentional source of RF energy, let us say. So that is also collected. That's what I mean by sub 1 gigahertz as the source, the second source here. You may also have other energy harvesters such as mechanical vibrations and other things, because one of the applications that this batch of students were looking at was actually structural health monitoring, for example, for a bridge. So they essentially used a slightly modified version of the IC that was designed by the previous batch of students, which are both done on a UMC 130 nanometer technology, which has the RF to DC conversion for FM bands, and it also the other for the higher frequencies and other bands. The plan was actually to have the matching circuits outside. The main reason for that is actually you can get better quality factor by having those components outside than inside an IC. And of course, the real estate is also was a major concern. So this is the overall schematic for the integrated circuit that was actually built. We could do some bit of power conversions and management using this circuit. So the plan was actually to have multiple to design a board which will have multiple ports for different, let us say, for different FM radio stations, so that we try to maximize the energy that is available through each of those bands that are available, or each of those FM stations that are available nearby. And we can also what we also tried to do was to see come up with several interesting innovations in terms of the power management circuits, because even from some of my colleagues from the power department here, they appreciated the fact that some of these concepts that we use here are quite unique, because that's not we the power electronics folks generally don't work at such low power circuits, at least here. So this, as I said, requires innovations in certain directions which are I would say not normal. For receiving the power from the energy from the RFID reader as a source. Here there is no RFID the RFID was not used as a communication device in this particular case. We are only using it as an energy source. the idea that we had at that point of time was that, if there is no other form of energy available, a user goes there and essentially drives the circuit using this source, and the you know you will be able to work without having batteries inside. So a worst case scenario, you could have these, obviously, in addition to other forms such as vibration and other things that are potentially possible in a bridge scenario. The sensor that we used was obviously is a strain sensor, and if you recall from one of my early slides, it actually required a very relatively high current. If you recall, it is like 1.3 milliampere current was needed to drive the strain sensor that was available. That was apparently the lowest power hungry one that you could actually get. The board that these students built is something like this. It has this energy harvesting chip in the middle. You have the RF off-chip components for the RF to DC conversion, and which is given into this IC. We had provision for two separate ports for the FM radio, and what you see subsequently are the power, some of the higher levels of power management circuits and cleaning circuits, so that you will be able to drive microcontrollers with which you could do the sensing operations. The completed board will be somewhat like this, and what they tried to demonstrate was actually what you see here. Um, a mobile application was also built so that we will be able to sense the data from these different sensors that could be done. And what you see here is an experiment where you actually put different weights on a cantilever, and the strain was measured using the strain sensor that you have there. So as I was demonstrating, you can go, you can combine power available from multiple sources if your electronics is, intelligent enough, and you take care of many of these aspects that you see here. The last case study that I wanted to discuss with you is about a charging station for wearable devices. We talked about it in the beginning. But the existing approaches for wireless charging are typically at very low frequencies in kilohertz to some megahertz, and are obviously all of them are happening by coupled transfer of energy, and are also limited by the distance between these two, let's say, coils or whatever that is, the antennas or whatever that is. So what we tried to do was to build a system at working at 2.4 gigahertz, wherein we actually tried to make a relatively compact system. And what we tried to do was to ensure that we will be able to confine the fields in a small region and provide sufficient flexibility to charge, wearable devices independent of its position, independent of its orientation, location, and various other aspects. So basically, it is a near field antenna design problem, where what we tried to do was essentially to ensure that we have somewhat uniform uh, uh, field intensity, so that we will be able to energize these, one of these devices. So the concept that we came up with was to essentially use two different antennas, and we have something like a cavity in between, and where the where we can do some changes in the antenna design to ensure that the uniformity of the field and its orientation can be somewhat maintained reasonably flat. So what it would involve, we should have a DC source, then obviously an RF source for 2.4 gigahertz, and then a power amplifier which is essentially split into these two antennas, and one could do several other improvisations further on to maybe even make an adaptive circuit which can actually where you can have a phase and amplitude control with which you can even locate the position of a device and do it. But we have not done any of those things yet. We actually try to build these antennas in such a way that we can have fields within and is somewhat independent of the position. And what it allows us is that we can put any device in there. So what we have tried to do is actually put a antenna and a rectifier circuit, and then connect it into the USB charging port of device here. As you see here, the watches are smart watches are being charged using the energy collected by the let's say the harvesting terminal that you see here. And this obviously, if you have to charge these devices, you have to give high voltages. So therefore, we need to have sufficiently high power within these particular antennas. So we had to use an amplifier to get the power level that you would need. Obviously, if you look at the overall conversion efficiency, it is poor, but we are still able to charge a mobile phone using this arrangement with the kind of power levels that we are using. So I think I'm pretty much in time. So to summarize my short lecture here, what we have seen is that most of the low power devices can actually operate at at certain intervals of time. They operate intermittently. So we basically can use this opportunity to store the energy over a period of time in some form, either in supercapacitors or some other forms of storage of energy. And we have seen that solar is available and available in plenty, but may have some limitations in certain scenarios. So therefore, RF energy harvesting or the wireless power transfer can become significant, can become particularly useful in certain special scenarios, right? So therefore, these technologies have a huge potential to energize Internet of Things in such a way that these if the devices and the communication technologies that we employ are of less power hungry, we might be able to charge them. And as you have seen with these several sets of examples that we have done over these years, it is obviously possible to build full system powered wirelessly and communicating wirelessly some kind of sensed information. So we have done with different wireless standards as well. As you have seen, we have done with the Zigbee standard, which is one of the popular standards in earlier years for wireless sensor networks. We have worked with Bluetooth Low Energy, and as I have also shown that this could be combined with the RFID tags. But what is critically important is a holistic design approach for the entire system end to end, so that we will be able to efficiently use the minuscule energy that is actually available. Um, I have a long list of students who have worked with me over these years for the prototypes that I have described to you, and several of my colleagues and some of my funding agencies. I acknowledge all of them. And I wish to thank you once again. I also thank the organizers for having me here for this platform. If you have any questions, you feel free to write to me in this email that I show here. Thank you once again.
Thank you, Professor. Thank you, Professor Vinay, for a wonderful talk on powering Internet of Things through RF energy. In the continuation of your talk, there are some queries. in the chat box of YouTube link. Some of them I would like to pass on to you. The first one is there any relationship between gain and directivity in case of RF energy harvesting and WPT?
Obviously, that is, if you have studied antenna theory, there is a direct relation between the directivity and the gain of the antenna. And I
Okay.
don't know whether you actually mean the transfer efficiency or the antenna efficiency in this particular case. But in
I
any
think
case, for a given
I think
antenna, obviously it is
okay,
related.
yes. Obviously, in case of traditional form of antenna, it is there. But I think he or she wants to ask in context of RF energy harvesting and WPT. Is that
Yeah,
formulation will be different for
right.
that?
Antenna remains the same. Antenna remains antenna, so therefore it has to.
Yes.
You have to work with the same thing. Yes.
Okay. Then second query, what do you think about MIMO antenna for RF energy harvesting and WPT?
So MIMO concepts are particularly useful in communication because it increases the capacity of communication by with an ingenious way of combining the spatial diversity here. But from wireless power transfer or energy harvesting perspective, uh, if you can obviously have multiple antennas, multiple rectifiers attached to these antennas, and combine the power at let's say at DC. So if you mean by having multiple rectennas by MIMO here, yes, that is a possibility, and I think I have also shown that in the example of the FM harvesting that I had.
Okay. The next query is we have designed a hexaband antenna accommodating 1 to 10 gigahertz band for RF energy harvesting application. Could you please suggest a way to design a rectifier circuit for this antenna?
So
Hexaband
if you
antenna.
recall, yeah, yeah,
Uh,
yeah. If you recall um, uh, the the matching circuit, one of the main functions of matching circuit, especially if you are targeting energy harvesting, is to have a high quality factor. And therefore, only if you design the matching circuit tuned to a particular frequency, you can expect to have that. Therefore, unless you have some ingenious way of building this hexaband matching circuit, it's not going to be working. And I don't see that to be an easy approach either. So,
okay.
you may have to see it very carefully. Yeah.
Next query is any government norms for energy harvesting and WPT in India or worldwide as far as health hazard aspects of RF energy harvesting or WPT on wireless body area network is concerned.
Yeah. So energy harvesting, you're only harvesting the energy that is actually available, otherwise. So we are not introducing anything new. So therefore, there is no new regulation that is to be considered. Whereas on the power transfer, obviously the transmitting station, whatever or transmitting device that you have, has to follow the norms, and we have to follow these for our own safety. And I strongly encourage to be limited within the power levels that it is there. So, for example, the last example that I shared with you, we try to ensure that the power that is fed to these antennas are limited to a watt, which is what your mobile phone would radiate at 900 megahertz.
Okay. The last query from audience side is, could you please suggest some company names fabricating commercial RF energy harvesting or WPT products?
I think there are several. I have not looked at it in recent years, but about 5 or 6 years back, before we were building the IC, there was this company called Powercast. But I think they had some arrangement with TI Texas Instruments subsequently. There were also, I think there is something called Spartacus, and probably there are more. I have not looked at it in recent years.
Okay. With these, like several other queries are there, but it will be difficult for handle all of them. I would suggest to all the registered participants to please contact concerned speakers. I would be sharing the official email of Professor Vinoy for your convenience. Later on, you may contact him, and I think Professor Vinoy would be happy to handle the queries based on this talk later on if any query comes from the participant sides.
Oh, definitely.
Okay. Thank you, Professor Vinoy, for sparing your valuable times and for accepting our invitation for delivering this talk. Thank you once again, and bye.
Welcome.
Okay,
You're
sir.
welcome.
Now you
Thank
please
you.
leave this presentation mode so that
I
next
thought I
speaker
have
should.
done that already. You must be able
Okay.
to take it now. Yeah.
Okay. Thank you. Thank you very much. Uh, Hello, everyone. And now I would like to take the privilege to welcome our next and last speaker of the day, Dr. T.R. Lenka, Assistant Professor at National Institute of Technology, Silchar, India. T.R. Lenka received the BE degree in Electronics and Communication Engineering from National Institute of Science and Technology, Behrampur, India in 2000. MTech degree in VLSI Design from Dr. APJ Abdul Kalam Technical University, formerly Uttar Pradesh Technical University, Lucknow, India in 2007, and PhD degree in Microelectronics Engineering from Sambalpur University, Odisha in 2012. Currently, he is working as Assistant Professor in National Institute of Technology, Silchar since 2012. He received Distinguished Faculty Award by NIT Silchar in 2019. He is also the recipient of Sir Vishwashraya Young Faculty Research Fellowship Award by Ministry of Electronics and Information Technology, Government of India in 2018. He is a senior member of IEEE and actively associated with IEEE Electron Device Society, IEEE Solid State Circuit Society, IEEE Circuits and Systems Society, and IEEE Photonic Societies. He has guided 10 PhD theses and 18 MTech theses under his supervision. He has co-authored around 75 research papers in several journals of repute, 8 book chapters, and 45 papers in IEEE International Conference proceedings. His research interests include hard nitride semiconductor materials and heterojunction devices for power electronics, solar photovoltaics, MEMS-based piezoelectric energy harvesting, and nanotechnology. Currently, he is handling 2 sponsored research project funded by DST-SERB under ASEAN scheme and CSIR on development of high efficiency perovskite solar cells. With this, I welcome you and invite you, Dr. T.R. Lenka, to start your talk.
Thanks, Professor Khan, for the nice introduction.
Uh,
Is it visible, Professor Khan?
no, your screen is not visible. I think on bottom side there is an option. Bottom side right corner. Bottom side right corner. Present now option.
Your entire screen. Share.
Now is it okay, Professor Khan?
Yes, yes, it is visible.
Should I start?
Yeah, please carry on.
Is it visible?
Yeah, yeah.
So good afternoon, my Indian friends, and good morning, colleagues of Canada. Thanks to the organizers for giving me this opportunity to present talk in 1 week Indo-Canada SPARC virtual workshop on RF energy harvesting system sponsored by SPARC. It's an initiative of Ministry of Human Resource Development, Government of India. And my today's talk is third nitride nanowires for solar energy harvesting. Myself, T.R. Lenka from NIT Silchar. The outline of the talk is introduction, status of the photovoltaics technology, nanotechnology and its advantages, beauty of third nitride and applications, third nitride nanowires, polarization charges in nanowires, multiple quantum well nanowires, then summary of nanowire solar cells, conclusion followed by acknowledgement. So in the introduction, the solar photovoltaics, the process of converting sunlight directly into electricity using solar cells, which are made from semiconductor materials. And it is a rapidly growing and increasingly important renewable alternative to the conventional fossil fuel electricity generation. And as all of us know, the silicon solar cells are dominant worldwide due to its low cost and its efficiency. However, new semiconductor materials and technology are being explored for next generation high efficiency solar cells. And out of them, peroxide solar cells, third, fifth semiconductor heterojunction solar cells, tandem solar cells, etc. And in this talk, I would like to introduce nanotechnology for efficient solar energy materials in gallium nitride materials. So let us look into some of the status of the PV technology very briefly. The first generation around 1980 started the single and polycrystalline silicon solar cells with a potential efficiency of 29%, laboratory efficiency of 26%, and commercial efficiency of 16%. However, it has some limitations like high cost, large area limitation, less flexibility, terrestrial applications, and poor radiation resistance. However, the second generation started in around 2002. It has potential efficiency of 23.5%, laboratory efficiency of 16%, commercial efficiency 10%, and it has certain limitations like low efficiency, toxicity, rare earth elements, terrestrial applications, and fair radiation resistance. Third generation started around 2007 with multiple junction intermediate band dye-sensitized polymer solar cells with potential efficiency greater than 50%, laboratory efficiency of 41%, and commercial efficiency of around 28%. It has certain limitations like high cost, high defects due to different type of materials, and difficult to fabricate. And it has applications in solar cell at space stations. So in order to apply the solar cells at space stations, it has certain characteristics like need to withstand against charged particles, micrometeoroids, hard UV radiations, and temperature, and high efficiency, lightweight, and longevity. These are the certain of the criteria of solar cells to be used in space stations. So let us look into nowadays very popular PARC structure of solar cells. PARC stands for passivated emitter and rear cell, or passivated emitter and rear contact. It's a new technology aim to achieve higher energy conversion efficiency by adding a dielectric passivation layer on the rear of the cell. Nowadays, industrial applications, these SPARC cells are very popular and has been used. And this is made up of mostly of dominating silicon material. So very briefly, we'll discuss how solar cell work. It is just like a simple PN junction. So a p-type material and n-type material of silicon, they are come in contact, and a depletion layer is formed, and UV solar radiations in form of photon it absorbing. Then there is a release of electrons from the valence band, and electrons start flowing through this load, and we are able for solar cell. We can see the electron and holes, they are being generated, and there is anti-reflecting coating because the photons which are observed in the solar cell, it should not be reflected back. So anti-reflecting coating is used, and in this way the solar cell works. So in this talk we will introduce instead of silicon material, gallium nitride technology and its nanowire, how it is grown for the solar cell applications. So there are certain fundamentals of solar cell. These are the performance metrics. It has short circuit current density, open circuit voltage, fill factor, and efficiency, quantum efficiency. So these are the performance metrics of a solar cell whenever it is designed. So these factors are when terminals are shorted, open circuit voltage when terminals are open, it is the maximum output voltage, and fill factor is the ratio of maximum power to the ideal power, and efficiency is the ratio of output power to the incident solar power, and quantum efficiency is the ratio of number of photons incident on solar cell to number of carriers collected from the solar cells. And this is a standard JV characteristics of a dark as well as light condition of a solar cell. This is a very standard. Now let us talk something about nanotechnology, because we are going to do the nanowires. So what is the need of nanowire in recent trends? So therefore we need to highlight some of the nanotechnologies. As we can see that in the pictures, there are 5 nanometer. This is the size of an ant, and 3 mm. This is one insect, and 1 mm. And that is another insect. That is we are able to see. These are we get these dimensions in our day-to-day life, just like ant, then fruits fly, then these are the very small insects. So they are going diminishing to nanoscale dimensions, because in a scale particularly we are able to measure 1 centimeter, then 1 centimeter is equal to 10 mm. So 1 mm we are very much acquainted, but whenever we are going down 1 mm to micro and nanometer, then it's very, very difficult for us to detect. But nanotechnology works in nanometer regime. So therefore I intend to realize that what is nanotechnologies. Then another example we would like to see, this is the eye of a fruit fly of dimension of 400 micrometer, then a red blood cell of 8 micrometer. So these are very, very difficult for us in the naked eye to detect. Now we can realize that a human hair that is of 10,000 nanometer wide, never thought of that hair, its width is 10,000 nanometer. So 1 micrometer is equal to 1,000 nanometer, and the virus its dimension is 50 to 100 nanometer, which is not detectable in our naked eyes. And DNA is 2 nanometer is the dimension. So these are the nanotechnology, means we are going towards miniaturizations in nanometer regime. Now talk about nanostructures, which are generally used in our nanoelectronics for getting new devices, new technologies. So nanoparticles, These are the carbon nanotubes and bulky bulbs of Fullerene structure. And quantum dots nowadays very much useful in various applications in science and technologies. The nanomaterial properties, it can be tuned by varying the size of the particle. We understood whenever the size of the particle is shrinking in a nanometer dimension, then the properties, it is changed, and the properties can be tuned by the controlling the dimension of the nanometers. And the properties in nanometer scale are thermal, melting temperatures, mechanical properties, electrical properties, optical properties. Now we would like to introduce various materials in our research. Is just like in third and fifth group elements. Third and fifth group elements are boron, aluminum, gallium, indium. As well as in fifth group, it is nitrogen, phosphorus, arsenic, and antimony. So as you know, silicon is elemental semiconductor. Germanium is also elemental semiconductor. But silicon is very dominating because of its very favorable properties. And in the coming years, we expect the silicon will be the dominating. Apart from that, many other semiconductor materials that are explored for different applications. Let us take one example, that gallium arsenide. This is one of the third and fifth material. Then gallium nitride, another very powerful semiconductor. In this talk, we'll focus on gallium nitride and its family of other nitride element compounds, just like aluminum nitride, indium nitride. Therefore, I intend to show this periodic table, that how important of different combination of materials which are doing wonders in electronics areas. Gallium arsenide is also very popular as a direct band gap semiconductor because of its high electron mobility, and this is useful in very high speed electronics also, but it has no polarizations. Polarization is one of the very unique material property in nitride semiconductor, in gallium nitride, aluminum nitride, and indium nitride, which is absent in gallium arsenide. Therefore, gallium nitride is very superior, that I can tell with respect to gallium arsenide because of this unique material properties. So gallium nitride, aluminum nitride, and indium nitride, these are third nitrides. They are doing wonderful electronic devices in our day-to-day life, in optoelectronics, in high-speed electronics, in photonics, and in high-frequency electronics. Then we'll talk about the advantages of nanotechnology, or we can say nanostructures. There are two diagrams. This is a cube of 10 centimeter dimension, another cube of 2 centimeter dimension. As you see, the 10 centimeter cube has a surface area of 600 centimeters square and a volume of 1000 centimeter cube, whereas a 2 centimeter cube has a surface area of 24 centimeters square and a volume of 8 centimeter cube. If we'll compare the surface to volume ratio, the surface to volume ratio of 10 centimeter cube, it is 0.6 to 1, whereas the surface to volume ratio of a 2 centimeter cube is of 3:1. So therefore, this is the advantage, that as objects get smaller, they have a much greater surface area to volume ratio, which makes technology at the nanoscale different from technology at the macro scale. So whenever the technology is going in nanoscale regime, so it has the advantage that its surface area is more with respect to its volume. So therefore, this is the advantages of nanostructure: large surface area to volume ratio. This is one of the very interesting example of zinc oxide, nano zinc oxide. This is work of Professor Jedel Wang of Georgia Tech, United States. So they have grown nanowires of zinc oxide. As you can see, one chemistry, but many shapes and many applications. As you can see, very wonderful. These are the pictures, scan electroscopy, microscopy pictures, ACM images. So they are of different colors, as well as they are useful for different applications. So therefore, it is very interesting to understand that of one chemistry but many shapes, and it has different properties and different applications. So in this work, we have introduced nano gallium nitride for solar energy harvesting applications. So nanowires, nanorods, or nanostructures in solar energy harvesting. So this is the main theme of this talk. Let us understand some of the work of many other researchers. And very recently, it has been published in various journals. They have done indium phosphide nanowires, silicon nanowire core, and indium phosphide cell, and ITO. And it is grown over P-type silicon wafer, and aluminum is back contact. And it has a current density of 14 milliampere per centimeter square. This is a silicon indium phosphide core cell nanowire solar cell. Similarly, this is one of the work of applied physics letters of zinc oxide nanowires, and nanowire have been grown over chlorine doped tin oxide glass. It is a dye sensitized solar cell, and one more is indium gallium arsenide nanowire solar cells, and it is of indium gallium arsenide N-type nanowires grown over P-type silicon, and aluminums are the contacts. Similarly, gallium arsenide nanowire tandem solar cell, mean two solar cells, they are added, or they are one over another is grown, so therefore it's called as tandem structure. Two structures they have combined into a single one, therefore it is a tandem solar cell. Gallium arsenide nanowire on silicon tandem solar cell, and as you can see, P-type silicon is the over which N plus gallium arsenide, then N-type gallium arsenide, intrinsic gallium arsenide, and on the top P plus gallium arsenide have been grown over. Therefore, it's called as tandem solar cells, and it has the JV characteristics, current density, voltage. So two structures, individual structures. So one is silicon standalone with the triangle size red color, and the other one is gallium arsenide standalone, and tandem is the full structure, and they have got open circuit voltage of 0.956 volt. So this is the tandem solar cell structure on gallium arsenide nanowire. Now we will introduce our nitrides. So the beauty of hard nitrides, as I said, the gallium nitride is very useful in various applications, like in high frequency electronics and power electronic applications, in optoelectronics, in photonics. So in this talk, we have introduced nitride nanowires for solar energy harvesting. Gallium nitride metal can be used in production of semiconductor power devices, as well as RF components and light emitting diodes. So nowadays gallium nitride is very much useful LEDs, that are called micro LEDs, and nitride based light emitting diodes. And gallium nitride has demonstrated the capability to be the displacement technology for silicon semiconductors in power conversion, RF and analog applications. As you can see, the nitride semiconductors are, they are compound semiconductors, aluminum nitride, gallium nitride and indium nitride. So whenever aluminum nitride and gallium nitride are combined, making a ternary, that is called aluminum gallium nitride, where X is the mole fraction, and whenever indium component is added, means indium nitride and gallium nitride, indium gallium nitride is made, and whenever aluminum nitride and indium nitride is mixed together, we are getting aluminum indium nitrides. So these binary as well as ternary semiconductors, they are all direct band gap semiconductors. They are doing wonderful in the applications like high frequency applications, LED applications, power electronic applications, RF conversion applications, and therefore I have talked the beauty of hard nitrates, and its structure is Urgite crystal structure. And as we see from the band gap versus the lattice constant, we can see gallium nitride and aluminum nitride, they are very nearly lattice matched, although there is lattice mismatch, but they are very nearly. Whereas indium nitride as well as aluminum nitride, a lot of lattice mismatch is there. So because of lattice mismatch, the surface roughness scattering occurs, but they are useful in many applications, and nowadays they are very much useful in light emitting diodes in the visible range. So there are certain advantages of gallium nitride. The advantages are categorized in one is power circuit, as well as another one is RF circuit. One is power supply circuit and RF circuit. For power supply circuit, the important figure of merits, they are called high operating temperature, high breakdown, and high maximum current density. And in we have compared three materials: silicon, gallium arsenide, and gallium nitride. And as you see, gallium nitride, it is covering a bigger range in the radar chart, and it means it can sustainable up to 400 degree Celsius, and breakdown voltage more than 300 volt per micrometer. So this is because of very wide band gap, and high maximum current density. We are getting 1.5 ampere per mm. So this is due to the factors including high carrier density, which is created because of polarizations, and high electron mobility. However, the electron mobility is very less with respect to gallium arsenide, but it is superior to gallium arsenide. Whenever we talk about the RF component, it has maximum frequency of oscillations. Therefore, we get high-speed electronics. It is due to the factors including high electric field saturation speed and low parasitic capacity. Parasitic capacitance is very less in the integrated circuit, and the noise factor due to factors including low carrier scattering. Scatterings are very less, and low RF losses. So therefore, noise factor is also very less. As we can see from the radar chart, it is 0.5 dB. So these are some of the advantages of gallium nitride useful in power supply circuit as well as in RF circuit. So some power electronic applications I will highlight very briefly. The power electronic systems for gallium nitride HEMT, that's called high electron mobility transistors. It is not limited to, but it is laptop power adapter. Nowadays, the power adapters in the laptop, they are very light instead of bulky, which were from the earlier technologies. They are very lightweight. It is converting our 230 volt to certain volt, maybe 5 volt or maybe 6 volt or 3 volt. Then it is useful in solar cell micro inverter. These micro inverters are nowadays very popular household appliances, and very commonly used. And wherever for power conversion we need the gallium nitride HEMT technologies. Then this is very popular in very advanced countries like electric vehicle charging stations. Means instead of these other fuels, electric voltage charging stations are useful for charging their vehicles. So the power module, in the power module, gallium nitride HEMTs are useful, as well as in data center, the power module in various data center servers. These gallium nitride HEMT are useful. Therefore, it is increasing the efficiency so that the power consumption is reduced. So if power consumption is reducing of a particular country, maybe 1%, so that a lot of electricity bill can be saved. So this is the way we can conserve the electricity through this gallium nitride technologies. Now, if we talk about the RF applications, the gallium nitride role is very pivotal. RF front-end transceiver is required for transmitting and receiving over the free space. It plays a very key role in communication systems, and because of this very advanced communication system in this pandemic, we are able to talk to the entire globe. People all over the globe, they can be connected through internet, and nowadays internet has played a very pivotal role for connecting people as well as for progressing the technologies. Instead of this pandemic, but still life never stops, it moves. So therefore, this is the technological advancement, and this gallium nitride is useful in our 4G 5G technologies. So LTE as well as WiMAX, and they are of 5 gigahertz. Then in defense systems, in data broadcast systems, so in all type of RF electronic systems, gallium nitride devices and its MMIC role is very important. So therefore, gallium nitride, I said that it is very powerful material, as well as its devices are very unique, and it is going to overcome the silicon dominating technologies. And 5G technology, which is coming in our day-to-day life, not yet introduced, but it is coming. So 5G is using gallium nitride. So that has been introduced here, gallium nitride applications in 5G technologies, because of high efficiency, because of high frequency of applications. It can be used as a oscillator, and ultra wideband linearization, as well as small package and high power deliver capability, and low voltage, small size and high linearization, and small size, compact and high temperature sustainability, useful in the automobile sectors, useful in RF electronics, because of its high temperature and high reliability. So the role of gallium nitride is useful in RF electronics, it is useful in power electronic applications, and it is useful in optoelectronics. So now let us talk about the potential material, indium gallium nitride. This is a mix of indium nitride as well as gallium nitride. But this PV technology, how they are picking a very important role for our solar cell applications, and these solar cells are particularly useful in space applications. So therefore, it is quite expensive, I can say. And this is the unique properties of this indium gallium nitride solar cell. It is having tunable band gap engineering. The band gap is from 0.7 electron volt to 3.4 electron volt. And the full solar spectrum photovoltaic material, with the entire solar spectrum can be observed, whereas in silicon technology, the entire solar spectrum is not able to be observed. Some of the solar spectrums, they are not observed by the silicon solar cells. So therefore, indium gallium nitride based solar cells, it is observing the full solar spectrum. That is one of the advantages. High absorption coefficient, high radiation resistance, which is therefore it is useful in space applications to tolerate various radiations, microwaves, and capable of being deposited with nanostructure. Its nanowire can be grown, and potential efficiency, and suitable for terrestrial and space applications. As we see from this diagram B, band gap versus wavelength, as you can see, whenever the X component of this indium gallium nitride, whenever X component is increasing, its wavelength is increasing, as well as band gap is decreasing. So therefore, band gap is 0.7 electron volt to 3.4 electron volt. Means the band gap of indium nitride is 0.7 electron volt, and band gap of gallium nitride is 3.4 electron volt. Let us look into some of the material properties. The material properties of gallium nitride and indium nitride, it is listed in this table, and it is low effective mass. So therefore, mobility is large. Because of the composition of indium, so it is optoelectronic property is increasing. So it is a direct band gap semiconductor, and band gap is 0.6 electron volt or 0.7, sometimes 0.66, and in gallium nitride it is 3.4 electron volt. And the substrates used for this third nitride nanowire growth, the substrates are useful as zinc oxide and silicon, and zinc oxide coated graphene, and somewhere used sapphire and silicon also by many researchers. However, there are certain challenges in indium gallium nitride based PV technology. The challenges are dislocation densities and lattice mismatch, indium phase separation and indium fluctuation, polarization charges, cost of materials. It is early stage of research, and growth of indium gallium nitride with entire compositional range means it's very difficult to grow the indium gallium nitride considering all indium contents. So performance degraded at high indium content. These are some of the challenges and still under research. And the unique properties of this indium gallium nitride are the polarization charges. The two type of polarization charges are there. One is spontaneous polarization and another one is piezoelectric polarizations. So indium gallium nitride layer typically grown on lattice mismatched gallium nitride. Stock of immobile charges at heterointerface is known as the polarization charges. This is the charges created at the heterointerface, and these are automatically created. So these are the unique properties of gallium nitride technologies. Here, two examples are taken. One is 0001 crystal orientation, and another one is 000-1 crystal orientations. So in the top structure, p-type gallium nitride, intrinsic indium gallium nitride, and n-type gallium nitride. So in between two p-n junction, we can say we have introduced one intrinsic indium gallium nitride material. So two type of polarizations. So when c-axis terminates at gallium polar, it is 0001 plane, and reverse polarization. So when c-axis terminates n polar, it is 000-1 plane. So the polarization charges are created at the heterointerfaces, and they are beneficial for the device applications, and which results into a two-dimensional electron gas at the heterointerface. And this two-dimensional electron gas is the heart of any heterostructure field effect transistor or HEMT. And here we have introduced some of the structures like nanowire structures. Two type of structure, one is axial and another one is radial structure, and these are normally grown on different facets and well controlled geometrical shapes, allows larger lattice mismatched heterojunctions without dislocation, and low plastic and elastic strain, allow high thickness for better light absorption, and high surface to volume ratio that we discussed, that for a nano where this is the advantages: high surface to volume ratio, possible to grow axially as well as radially, and low piezoelectric polarization charges, low non-radiative recombination centers. So radial, inside it is called core, then cell and cell, whereas in axial, one over another layer is grown. In the bottom it is p-type, then top it is n-type, and it is by mistake it is written p-type GaN, and intrinsic, and it is sandwiched between the two p-type and n-type gallium nitride. Now let us make a comparative analysis of planar as well as nano disk and nanowire solar cells. And this is the work, it has been published in 2017 in superlattice and microstructures. So the comparative study between planar, figure 1 is planar, then figure 2 is nano disk, and figure C is core cell nanowire structure. And its thickness of n-type gallium nitride is 40 nanometer, and thickness of p-type gallium nitride it is 100 nanometer. Thickness of indium gallium nitride intrinsic it is 6 to 200 nanometer. In between them it variation has been done, and contacts are nickel and gold, 5 nanometer each, and the defect density is introduced from literature at 10 to the power 17 and 10 to the power 14, and core cell nanowire it is 10 to the power 12. So these are the three structures. We have done the simulations of these three structures. These are the carrier dynamics in planar. Figure A is planar, figure B is the nano disk, and figure C is the core cell nanowire solar spectrum, a solar cell at 100 nanometer, 150 nanometer, and 180 nanometer indium gallium nitride thickness. So indium gallium nitride thickness variation has been done from 100, 150 as well as 180 nanometer. So these are the energy band diagrams. It is taken from the simulator, that we could able to see that in core cell there is a heterojunction is created between indium gallium nitride as well as p-type gallium nitride, and where at this heterointerface the polarization charges are created. This is short circuit current densities of the three structures at different indium contents: 10%, 20%, 30%, 40%, and 50%. In order to find out which indium content is best suitable for high efficiency for this planar structure, as well as nano disk structure, as well as the core cells, nanowire solar cells. The thickness of nanowire is varying from 0 to 200, as you see from the plots. And open circuit voltage, the results are finally listed in a table for comparative analysis at the end of this particular discussion. And the open circuit voltage of, again, the three structures, planar, nanodisk, and core cells nanowire solar cell, which is the figure C, and the thickness is varying from 0 to 200 nanometer in all the three cases, of indium content of 10%, 20%, 30%, 40%, and 50% of indium content. So fill factor is also shown for the three structures for the same set of indium contents. As you can see, the fill factor is increasing from the figure. If you can realize without looking into their values, the fill factor is, in case of nanowire solar cell, it is increasing because it has the advantages of surface to volume ratio, and the electric field and the total recombination rates of the three structures, planar, nanodisk, as well as nanowire solar cells. We want to compare which structure is beneficial for more absorption, more photon absorptions, more conversion of charge carriers into electricity for 100 nanometer, 150, and 180 nanometer indium gallium nitride thickness. And these are total internal quantum efficiency for the three structures. The blue color is planar. As you can see, it is 60%, around 60%, 62, 64%. And nanodisk, the red color, it is of 70%. And nanowire, black color, that is more than 75%. The quantum efficiency is more in case of nanowire, core cells, nanowire solar cells. And finally, whenever we look at the important performance parameters from the JB characteristics, the figure 1 is the planar structure, nanodisk structure figure B, and core cell nanowire solar cell figure C of 100 nanometer to 200 nanometer indium gallium nitride thickness variation. As you can see, the power density in the core cells nanowire is more, around 6.4 milliwatt per centimeter square, as well as the current density is also more, around 3, near to 3, with respect to the other two structures. Now these values are listed in this table for better comparison. The core cells nanowire solar cell can accommodate higher thickness of indium gallium nitride layer to accommodate 90% of the photons from the sunlight, and indium gallium nitride layer in planar and nanowire disk are limited by surface recombination and polarization charges. The current density of core cells nanowire solar cell increases due to higher collection of the carriers, and the staircase type JV curve are observed in planar and the nanowire type of solar cells. This is stepwise staircase type of JV characteristics. So we see from the listed performance parameters, performance metrics, the CSS, the core cells nanowire, it is giving better efficiency, as well as fill factor is more. Open circuit voltage, it is although nearer to nanodisk is more in case of open circuit voltage, and current density is more, and it is the width of the indium gallium nitride is 180 nanometer is fixed. So from this simulation experimental analysis, through simulations, we observe that nanowire, it is giving better results. So definitely nanowire is having potential research area that it can give better results for our solar applications. So that is the theme of this particular talk. So in this way we have proceed. So nowadays these nanowire solar cells are very high demand by the worldwide researchers. So therefore we have taken up this research into further extension. We have made the strain induced polarization charges and we have exploited their characteristics in triangular nanowire solar cells. And in this talk also we have discussed hexagonal solar cells, because whenever the gallium nitride with indium components it is grown, it is making two type of structure in experimental growth. One is triangular structure and another one is hexagonal structure. And the triangular structure and hexagonal structure, it is their characteristics of the growth, means depends upon many parameters. So two type of structure it has been observed from literatures. The growth is occurring, one triangular as well as nanowire, hexagonal nanowire. So therefore in this talk we have concentrated on triangular as well as hexagonal nanowire solar cell of this material. This work is published long back in 2017 and during our early research in this gallium nitride solar cell. So it is published in IEEE Journal of Quantum Electronics. So therefore we thought that yes, definitely there is a potential research avenue in this particular solar cell applications. So depending on the growth of technology, triangular nanowire solar cell may have either many crystal orientations like 0001, 1 minus 1, 0 minus 1, as well as minus 1, 1, 0 minus 1. Likewise, many crystal orientations. In this way, the growth is happening depending upon the growth process conditions. And the growth of nanowire via VLS, vapor liquid solid technique, yields triangular nanowire with the internal apex angle of 62 on either side of crystal planes like 000 minus 1 and 001 plane. We can see this is one model we have developed, that is of the structure PIN. If you go from core, cell and cell, or if you can come from outer cell to the inner, that is NIP structures, and the dimensions we have fixed it depending upon many research we have investigated from researchers of the worldwide experimental results. So, and the facets are also shown here of many crystal orientations, just like 000 minus 1, 1 minus 1, 0, 1, and we have got the interfaces to realize that what is happening in the interfaces. So these are the some of the stiffness coefficients in indium gallium nitride mismatched layer on gallium nitride layer as a function of the inclination angle and of different indium content, just like 0.1, 0.2 as well as 0.3. Means there is some physics happening at these interfaces that is very peculiar to understand as well as to investigate. These are the two diagrams. Very interestingly, it has been drawn, taken out from these simulators, and it is very interesting to see that how it is happening. Both are symmetrical to each other. So these are the net polarization charges composed of spontaneous as well as piezoelectric polarizations. At one is cell, means one interface, another one interface is core cell, and another interface is core cell, means p-GaN and i-GaN. p-GaN and i-GaN means this is core cell. So at this interface, core cell, and another one is outer interface. So cell is the outer interface, because outer is n-type gallium nitride and the cell is indium gallium nitride and core is p gallium nitride. So whenever we have taken the cord there, then we could be able to understand, yes, there are some polarization charges at the interfaces, and the polarization charges at the two interfaces, they are symmetrical to each other for the indium compositions from 0.1 to 0.3 variations. And this same in the same polarizations we have understood in a different diagram. They are also very interesting to see that the polarization charges at the two interfaces. One is at the towards the bottom, and another one is towards up. And in the figure A and figure B is also in the same way. One is peak going upward as well as peak going downward. Means these are the polarization charges found out at these interfaces. So overall polarization field of N-type gallium nitride, indium intrinsic gallium nitride, and P-type gallium nitride core cells as nanowire solar cell along the interfaces of vertical cut at plus minus 180 degrees and 0 degrees respectively are realized, and the polarization charges at 0 and 1 plus minus 180 degrees are opposite to each other in polarity along the two cuts, and due to compression and expansion of indium gallium nitride layer above and under the p GaN and n GaN layer, so therefore we could able to investigate the polarization charges at the interfaces, which are useful. And that same thing also can be realized at these interfaces in terms of electric field of this indium content 0.1 to 0.3. So there we can see one peak is observed at this interface and another peak is observed in another interfaces. These are the electric field. This electric field is in a peak at these interfaces. So these are at these two angles at 0 degrees and another one is plus minus 180 degrees. It means at two cuts, one is core and cell, another one is cell. One is interior and another one is exterior. So these are the same electric field and the total recombination rates. They have been observed from this simulation analysis. And some of the energy bands at these interfaces. Energy band diagram of this nanowire solar cell are 0001 facet with 10%, 20% and 30% indium compositions under forward bias conditions. And these are also similar type of energy band diagrams at different place of cuttings that we can see from this diagram of this triangular solar cell. This is single solar cell. Energy band diagram of nanowire solar cell at 1 minus 101 facet with 10%, 20% and 30% indium composition under forward bias condition. This is another cut at another location. Energy band diagram of nanowire solar cell at 000 minus 1 facet, 10%, 20% and 30% indium composition under forward bias condition at plus minus 180 degree facet. And finally the objective, whether it is working as a solar cell or not, it is having the performance parameters is meeting to our requirement or not. It has been analyzed from the JB characteristics. Figure A is 10% indium content, figure B is 20% indium content, figure C is 30% indium content of the structure is. This is the nanowire, that is outer cell it is N GaN, inner cell it is indium gallium nitride intrinsic, and core is P-type gallium nitride. So therefore name is core cell nanowire solar cell with facets 0001 facet and 000 minus 1 facet under AM atomic mass 1.5 illumination of the solar spectrum. From a layman point of view, whenever we look at these three pictures, we can see figure A is better because its current density is more with respect to figure B, 20%, as well as with respect to figure C. From here we can realize that whenever we are increasing the indium compositions, the performance is degrading, as well as from the power density. From the power density, as you can say from the right hand side, power density is more, around 4 milliwatt per centimeter square in case of 10%, as well and for other cases it is nearer to 3, and whenever 30% indium compositions, it is around below 2 milliwatt per centimeter square. These are the JV characteristics, and the performance metrics are summarized in this tabular manner of a single nanowire solar cell. The performance parameters are the open circuit voltage, the current density, the fill factor, and the power conversion efficiencies. The reference is from a literature, that is they have taken 27%. We have taken three indexes, that indium content 10% and 20% and 30%, as we have observed. Let us look at the fill factor. Fill factor in the reference, it is 56%, and we have obtained 93%, and one is 89%. Another crystal orientation. With respect to the others, it is the highest. If we talk about the current density, is more, 1.6 milliampere per centimeter square, and open circuit voltage is 2.5. In literature, it is 1 volt. So 10% is favorable for us. So therefore, 10% can be considered for a single nanowire solar cells. Now we have done little modeling on the polarization charges in triangular as well as in hexagonal nanowire solar cells. We have introduced the hexagonal nanowire solar cells over here. We have developed models as well as we have made some simulation work. And finally, we have we will discuss some of the performance metrics summarizing the three different two structures, triangular as well as hexagonal nanowire. And these are the works are published in 2019 in solid state electronics, and in 2017 it is published in IET Micro Nano Letters. So these are our success steps towards this research gallium nitride based solar cells. So therefore we are confident enough that we are going in a right research area. So the hexagonal nanowire solar cells and one is triangular nanowire solar cell, its crystal orientations have been shown. Hexagonal nanowire consists of 6 non-polar facets as side wall, and triangular nanowire consists of 3 facets having 1 polar and 1 reverse polar facet and the 2 semi-polar facets of the core cell. As we can see from the center, it is core, then shell, indium gallium nitride, and another cell is outer. So therefore it is called core cells. So whether it is a hexagonal or triangular, the pattern of the core cell is same. That is, inner it is p type, outer it is n type, and in between them the intrinsic it is indium gallium nitride. It is a PIN from core to cell, or cell to core, it is NIP structure. So the polarization charges are created at this nanowires at the interfaces. The 6 hexagonal urgite crystal structure having the facets 0, 0, 0, -1 and 1, -1, 0, 1 and 1, -1, 0, 0 facets are shown here. And from this plot we can understand some of the spontaneous as well as piezoelectric polarization charges of this core cell gallium nitride and indium gallium nitride, or cell indium gallium nitride and n-type gallium nitride interface along the inclination angle of 0 to 180 degree with indium composition of 10% to 20%. So there is a variation from 10% to 20% in these two structures. The polarization charges spontaneous as well as piezoelectric. So the left hand side, the spontaneous polarization is shown here, as well right hand side is the piezoelectric polarizations are shown here. And these are similar type of structure, symmetrical of this total polarization of this triangular, that already in previous discussion also we have done it in core cell as well as cell inclination. They are symmetrical to each other. The total polarizations, if we consider total polarizations at various angles from 0 to 180 degrees for different angles from 0 to 180 degrees. So broad range of degree of strain relaxation are considered, and it is difficult to assume a constant degree of strain relaxation at nanowires. However, in general, higher degree of relaxation greater than 0.6 are considered for nanowires. Looking into many literatures of the experimental work, these are some of the energy band diagrams at different planes. So these are the PIN structure from right to left or from left to right, NIP structure of many crystal orientations. They have been shown here. The potential well is very important. This is happening at the interface of the conduction energy band. This is the discontinuity of the conduction energy band because of this band gap engineering, and where the polarization charges are gathered, and it is forming a two-dimensional well. So potential well at the conduction band at this n-GaN interface with different degree of relaxation. And second one is the enlarged version, means this is enlarged how it looks, that have been shown here to understand. The electric field at the interfaces, the electric field increases with the increase in the indium content along the 001 plane, and electric field are negligible along 0001 facet and reduces with increase in indium content. And indium content 20 to 40% are plotted here. It's a two-dimensional electron gas. We can better understand of the subbands which are created at the interfaces. It explains the position of the electron, the probability of finding electron at this interface. So the subbands are created. It means there are electrons which are generated because of these polarization charges. So 2D is created due to the conduction band discontinuity at the heterointerface of GaN in GaN. So Eigen wave function and Eigen energy potential, energy level in the potential well at n-GaN IGaN interface. It means cell-cell interface it is shown for 20% as well as 40% indium content. So one is 20%, another one is 40% indium content. Two figures are shown here. And distribution of electron and hole current densities for many facets as well as for different indium contents are plotted here. Finally, we'll see the performance parameters of these two hexagonal as well as triangular nanowire, single nanowires. As we can see from this plot, the open circuit voltage of triangular nanowire is 2.2 voltage, whereas for hexagonal it is 2.1, and for 40% it is 1.8, and hexagonal 40% indium content 1.6, current density is 1.6 in case of triangular, 20%, and hexagonal it is 1.48 for hexagonal nanowire. Fill factor is 90% in triangular, 20% indium content, and hexagonal it is 89. Power conversion efficiency is 3.18% for 20% of indium content, and same 20% indium content of hexagonal it is 2.788. So this is for single nanowire. So from this performance parameters we can understand that this triangular nanowire is better than hexagonal because its efficiency is little bit more, fill factor is more, and current density more, and the open circuit voltage is also comparatively more in case of triangular nanowire solar cells. So now we have introduced many quantum wells in between this core and cell. So therefore this nanowire is called as multiple quantum well nanowire solar cell. So gallium nitride, indium gallium nitride, and gallium nitride multiple quantum well nanowire solar cells. So we would like to see the quantum wells which are formed at this interface, cell-cell interface. So therefore it enhances the electron mobility because electrons are created at this interface because of this two-dimensional electron gas property and because of these polarizations. So therefore we have introduced multiple quantum wells at this interface for better efficiency. So therefore this name of this solar cell is called as multiple quantum well nanowire solar cells. As you can see here, we have introduced 7 quantum wells. So 7 gallium nitride of 7 nanometer thickness and indium gallium nitride 3 nanometer thickness are incorporated along the radial direction of the triangular nanowire solar cell. Nanowire with both 0001 and 000-1 facets are considered here, and as we can see that 7 number of quantum wells have been introduced in between core and cell for maximum electrons generation at these wells, and this is the work is published in IEEE Transactions on Nanotechnology in 2018, and we can show here the polarization charges in the multiple quantum well from this picture. So without going in detail of its technical, as you see from the picture, it is very, very interesting. So they are symmetrical to each other, means one is positive peak, another one negative peak. Again, repeating in a cyclic way, positive peak and negative peak, because 7 quantum wells are introduced at this interface between core and cell. So therefore, they are looked for, they are shown for 2 different facets. One is opposite reverse polar, and another one is polar, 000-1 and 0001 facets of 7 quantum well indium gallium nitride multiple quantum well with 10% indium content is considered. And the multiple quantum wells are also shown here in terms of energy band diagram, and it has been also enlarged. The enlarged view are shown in the bottom respectively. From the that we can see the multiple quantum wells. So they are created at these interfaces of these 10% indium content in all the structures of various facets are considered, and the multiple quantum wells, the electric field at this multiple quantum wells are shown here at various distances from n-GaN to p-GaN. So left hand side n-GaN and right hand side we can see it is p-GaN, and we can see the multiple quantum well with electric fields are plotted in 0001 phase -1 facet and 0001 facet best nanowire with 10% indium content. Now finally, the JV characteristics we can observe of the 2 facets, 0001 facet and 000-1 facet, under atomic mass 1.5 spectrum of illumination of 10% indium content of this N gallium nitride and indium gallium nitride and gallium nitride. So the 4 Celsius nanowire cell, we can see the current density is, in case of 001 facet, it is around 4 milliampere per centimeter square, and power density is around 10 milliwatt per centimeter square. In the voltage range is 2.5 volt, and the 000-1 facet, it is deteriorating. From the plot we can see, and the performance metrics of this nanowire solar cell is summarized here. The parameters: open circuit voltage with 000-1 facet is 2.1, whereas the 001 facet is 2.41. The current density is 4, and the other facet is 3.6. Fill factor is 94, whereas the 001 facet, it is deteriorating 47% fill factor, and the power conversion efficiency is 9.81 of a single nanowire 000-1 facet, and whereas it is deteriorating it with the 001 facet 4.21. That is the summary of this multiple quantum well solar cells. Now this is summarized here, the entire research whatever presented so far. In this summary you can see we are studying indium gallium nitride based solar cells. It is of 3 types. One is planar solar cell, one is in the middle it is core cell nanowire solar cell, and in the last it is nano disk solar cell. So if you see planar solar cell, which we have seen in the early of our talk, that is fill factor 82% of a single nanowire single planar structure. It is efficiency is 1.8 of a single structure. It's very, very less. So next we will move to nano disk solar cell. Fill factor is 87% and efficiency is 4.28. Means if you compare between planar and nano disk, so nano disk is better because of its efficiency. Now let us come to the core cell-less nano-air solar cell. Our entire research is based on this core cell-less nano-air solar cell. Fill factor is coming 91%, 91.6%, and efficiency is 6.46%. This is the very simple core cell-less nano-air solar cell. And whenever we further analyzed its hexagonal as well as triangular nano-air structure cell, hexagonal nano-air structure cell give 89% and efficiency is 2.7, which is very less. Whereas triangular nano-air solar cell, it is of two types. One facet 00-1 and another facet is 001 facet. As we see, 000-1 facet is giving better with respect to 001 facet. One efficiency 3.8185% and another efficiency 2.96%. So these are the simple triangular nano-air solar cells. Now, whenever we have introduced quantum wells, so we have done some modeling of stress and strain in nanoairs and modeling of polarization charges in nanoairs, and we have introduced multiple quantum wells in this triangular nano-air solar cell. Then we could able to get a fill factor of 94.34% and efficiency of 9.82%, around 10% efficiency in a multiple quantum well nano-air solar cells. So that is the achievement of this research of from a single gallium nitride based core cell-less nano-air solar cell, introduction of multiple quantum well, which gives us around 10% of efficiencies of a single nano-air. If we can able to make an array of nano-airs, then efficiency can be very more. So now we would like to conclude this talk that indium gallium nitride based multiple quantum well solar cells are efficient and very important potential area of research, because these type of solar cells are not for day-to-day purposes. These are for some special applications in mostly of space applications to be used in satellites, in spacecrafts. And the triangular nano-air solar cells are efficient than hexagonal nano-air solar cells, and due to the favorable polarization charges along interfaces of each quantum well, carrier escape and separation process are quite more efficient than thick indium gallium nitride layer. And it is interesting to observe a remarkable efficiency of around 10% with 10% indium content in 000-1 facet, whereas the triangular nanoair with 0001 and other crystal orientation based facets show efficiency of less due to the detrimental effect of the polarization charges. So this is the conclusion of this talk, that this nanoair based solar cell, gallium nitride based nanoair solar cells are a potential area of research for getting better solar efficiencies, for solar conversion, and for high EPC power conversion efficiencies. So that is one of the potential research area of research that can be done, and people are working on it. And however, it has some of the challenges. The experimental analysis, the experimental making of these nanoairs are challenging, but still it is not difficult. Only depends upon the facilities, depending upon the research investigation, how much we are investigating. And this work is published in IEEE Transactions on Nanotechnologies in 2018, and this is one of our achievement of our research, is getting more citations nowadays. And I would like to acknowledge my PhD students already passed out, Mr. Soumya Ranjan Rautrai. He has done this research on modeling and simulation of gallium nitride, indium gallium nitride based core cell-less nanoair solar cell for next generation photovoltaics technology. And another PhD scholar, it is on silicon based solar cells. And I would like to thanks for listening to me, and I am very thankful to the organizers for giving me this opportunity to present my research in this international forum. Thank you all.
Thank you, Professor Lenka, for this wonderful talk. Now come to the query part from participants. The first query on your talk is, what do you think about fabricating and characterizing commercial PV technology based energy harvester at low cost?
Yeah, I would like to take up this question. That definitely it is a challenging affair, because the fabrication is very costly, as well as it depends upon all research, and time will tell that how we can able to give very cost effective solar cell to the society. And I said it is not for day-to-day life applications. It is because of its cost effect, it is mostly useful for solars, for space applications.
Okay. Next query, what is the best simulation environment for nanowire based harvester? Simulation environment for nano based
Yeah,
harvester.
it is very interesting question. For the entire research we have done on Victory, and Victory is a very industry based means tool, and it is not actually mostly available in all places. So mostly industry applications, they use Victory from the Silvaco CAD, and I will suggest the Victory is very popular for this nanowire solar cells for compound semiconductors like gallium nitride and gallium arsenide type of materials.
Okay. The next query is, what maximum efficiency is achieved by nanowire solar energy harvester till now in the open literature?
Many applications, many literatures are there. Many people are working on gallium arsenide and gallium nitride on research. Some people are doing indium phosphide, but I will tell you, nobody has crossed 30% of efficiency, because only the peroxide material, it is giving us 30% of the efficiency as per the um, literatures.
Okay. Is the bunch of nanowire is nano inductor?
Again, the question.
Is the bunch of nanowire is nano inductor?
No, I cannot answer this question.
Okay. Let us come to the next query. Why the efficiency is so less in these proposed solar cells? I am asking in this question with respect to silicon crystalline solar cells.
Yeah, this is a material. No, the efficiency, I am not telling it is less, because whatever investigation is done, it is just like one solar cell, one nanowire, one nanorod, that you must understand. Means one nanorod means one dot pen you have make it vertical. That's the thing. We have not made a array of nanowire, because this is the constraint of this tool, that no tool is supporting for making array of nanowire so far, that as per our knowledge.
Okay. It is possible to fabricate nanowire in India?
Nanowire fabrication, it is possible everywhere, not only in India. If you are having a low cost equipment, you can make nanowire, but what nanowire you are making, it is a question mark. Whether you are making a silicon nanowire, zinc oxide nanowire, so they are very simple. We are also doing nanowires in our other research, in our universities, in our collaborators with NIT Manipur, as well as in every places. So wherever you are having a e-beam evaporator, you can fabricate nanowires. But what material you are using, that is important. And I am telling you, gallium nitride nanowires, it is very expensive, and expensive because of the equipment and the laboratory establishment.
Okay. Now, last question is, would you suggest some professional company who are doing the like prototype in this solar energy harvester?
This is an interesting question. So far, I have knowledge on gallium nitride based manufacturers, but the manufacturers are of RF components or power electronic applications. Many companies are there, but for energy harvester, I have very little knowledge on this. The company who are making, no company in India, I am telling you, but international companies may be there. But I'm telling you, these are all on research till now. So therefore, from the literature, if you can find, the efficiencies are also very less. So therefore, till now, the nanowire modeling is also very new. It's very difficult for understanding the modeling aspect. So I don't think any company nowadays has plunged in for making nanowire energy harvester. These are all under research.
Okay. Now I think what maximum queries which were relevant to your talk, you have nicely handled all of them. With this, I thank you once again for this wonderful talk. And now we are coming to the conclusion side of this second day session of this workshop.
Okay, thank you, Professor Khan, for nice arrangement for giving me this opportunity to present myself and my research into the international forum. And I am highly thankful for the organizers as well as the international community, means the University of Queen's University of Canada and NIT Silchar and D2 India for giving me this best platform to put forward my research to the in international level. Thank you.
Okay. Okay, sir. Bye. Thank you very much. Now, on the behalf of organizing committee, I thank you all, the participants, for attending this second day of all three lectures. Now, finally, we will be meeting again tomorrow at 6 p.m. for third day of lecture. Before concluding myself, there is a minor change in tomorrow's session, that lecture number 9 and 15 are interchanged due to some problems on the speaker sides, and similarly lecture number 10 to 13 are also interchanged. The rest of the things are same, which we have already circulated to all of you. With this, thank you all once again. Bye bye, good night, good morning, good afternoon to all of you. See you tomorrow at 6 p.m. Bye.
Thank you. Thank you.